Here, the role of TNCs. So we'll continue the discussion. So again, as I was talking about in the last session, TNC and the role of transportation network companies within the transportation systems has increased significantly. There was a setback because of COVID, because of social distancing, everything went down. But as you can see with new data in here for New York, it has reached back to pretty much pre-COVID levels in New York. In this, we don't have the data for 2022, 2023. We're doing only up 21, but we are seeing that the rapid pickup back to pre-COVID levels. In fact, the trends are such that they'll go higher than pre-COVID levels in few years. So TNC is here to stay, and it will be an important component. So what we are looking at here is how can we assess how TNC is serving the transportation system. So previous research focused on what is happening because of TNCs, are what are the locations that are served by TNCs, what are the social impacts and so on. So there were some research efforts showing that vulnerable communities are not being served, there is discrimination in terms of ethnicity, income and so on. And also there were some studies saying that TNCs are adding additional miles to travel because a lot of times they travel empty, and also there are other implications of that. And there is also reduction in public transit, why TNC is drawing some of its trips from traditionally public transit, especially when the weather is bad. It starts raining, people who typically travel by bus consider using TNC as an option when the weather is bad, and so those things have been reported in the. But what was lacking is what is the impact of TNC in the context of the overall transportation. What is the overall transportation demand in a particular location? How much of that is served by TNC and what governs it? So we wanted to look at that aspect. So what we did here was we focused on examining TNCs in the context of overall transportation demand. We developed a metric to identify the imbalance between overall transportation demand and TNC demand. Again, the reason I'm talking about this specific study about TNCs is the same method can be utilized to look at how public transit or any shared mobility mode interacts with the rest of the travel. So this approach is more that way. We looked at again, it's when the metric is developed, you want to understand the relationship of the metric with the host of explanatory variables. We're trying to see whether it's the income, whether it's the employment, whether it's the population density, whether it's transportation infrastructure that is influencing this relation. So that's why a set of independent variables were considered. I'll talk about them as we go forward. And so that we can identify, the idea is to apply for any urban to identify special pockets or speed pockets where there are underserved or overserved by TNC. So again, as we go ahead, we can see this. So what we did here is we looked at the city of Chicago. All the travel data was aggregated at the census tract level. So we have TNC demand at the census tract level. We also have overall transportation demand at the census tract level. So any thoughts on how can we get the overall transportation demand for an urban region? What would we use to get that? You have to use a travel demand model, right? So maybe you can use a household travel survey based travel demand model that will give you information on the actual demand, overall transport demand across the urban region and any resolution mode, right? So what we did was we got these two variables. So for every census tract, we have two information. One is what is the demand for TNC in that census tract, and what is the demand for transportation. Okay. Now both of these numbers are not directly comparable, right? Because again, this is the total demand. So total demand includes walk, bike, auto travel, commuter, all of that is included. All of that is included in the overall transportation demand. TNC demand simply looks at how many people are using Uber or Lyft in Chicago. So we do not want to the numbers directly are not comparable. So what we did was we ranked them in descending order, if you will, and we partitioned each tract based on a decile. What we are looking at is we have 800 census tracts. The top 10 census tracts go into decile 1. Top 8, sir. So we organize them into 10 groups in ascending order. The same thing for the overall transportation demand also. And then we looked at how do they differ. So for example, there is a census tract, it happens to be in the second decile for transportation demand. So what that means is there's a lot of demand for TNCs relative to the rest of the city in that census tract. Now then we compare it to where does it fall in the overall transportation demand. So is the overall transportation demand also very high? So then it is not underserved or overserved, right? So if my census tract falls in the third decile for TNC and falls in the third decile for overall transportation demand, it's represented. What all it tells you is we have good demand in TNC, good demand in overall transportation demand. But now if you see a zone or census tract which falls in the first decile for TNC but falls in the eighth decile for transportation, that tells you overall demand is low, but TNC usage is very high in that. So that identifies an imbalance where that census tracts are overserved by TNC. Okay? Again, just by identifying this, we are not trying to say it's bad to be overserved. We are just trying to identify a difference between overall demand profile versus overall transportation network company demand. Okay? This is just to identify the difference. So we rank them in this manner by deciles, rank 1 through 10, and then we take the difference of the ranks. Okay, that's what will give you an indication. So here we did this. So we created 5 groups. Okay, we observed the census tracts and looked at the distribution, and we used it to create these 5 groups. So if the rank of overall transportation demand minus rank of TNC demand. So what this tells you is the overall transportation demand is lower, the rank of the transportation demand is lower, rank of TNC demand is high. Okay, so this is what we labeled as TNC surplus. So this is very high TNC surplus. So we call this high TNC surplus. So balanced when there is not much difference. Again, TNC deficit, high TNC deficit. Again, the same idea. Looking at the difference of these two numbers, keep moving. So the difference is -1, that goes into TNC surplus. No difference, that tells you that both are in the same. If TNC is in the 5th decile, demand is also, transportation demand is also 5th decile, that tells you it's a balanced system. There is an expected number of TNC trips that should happen. What is happening? This is where you start seeing deficit, where you have a lot of transport demand, but there is not enough TNC serving those things, or TNC is underserving those things. Another thing is overall transportation is very high, but TNC demand is low. Now, is labeling a census tract high TNC deficit, is that bad? What would this be useful? So now I have, let's say, 800 census tracts in Chicago. As I showed in the table there, 200 are high TNC deficit zones. So that's like about 25% of the zones are in that census tracts, and so all of 25% of the city is bad. Would that be conclusion will reach? I'm asking that question, so it's not. So why should it? What are some important aspects to consider when you look at deficit? So some census tracts are expected to be in deficit. Think about suburban communities where people own cars. There is a lot of demand coming from those because they're working, they go to office, they drive and all of that, or use public transit. But because they are regular commuters, they have plans of how to get to work. So there are households with 2 cars and 3 cars, they are not going to use trains, right? So there will be some pockets with high vehicle ownership, high income neighborhoods where there is a lot of transportation demand and very little TNC demand. That is fine. Those are not problem census tracts, right? So we have to be careful. Just because we label that a high TNC deficit, that does not automatically make it a bad census tract or a census tract that has problems. We're not trying to suggest it. All we're doing here is figuring out, okay, where are the pockets where there is a deficit And then we will further investigate. We look at, okay, what is creating this deficit? Are these census tracts people who live in communities who don't have cars, are captive riders and would benefit from TNC? That would be something we need to. So we need to study that further as we go forward. So these are the 5 categories we created. Again, there is some discussion on when we are looking at the deciles. You can actually have a score in each of the deciles, and we could directly take the difference of the deciles, right? We can take the difference of where does this fall and where does that fall, and study that also. We wanted to go with the categories. I think it's easier for planning this categorization. Once we create these 5 groups, rather than talking about an arbitrary score, this I think gives them a sense of, okay, oh, these are census tracts that are balanced, these are census tracts that are not on this side and on that side. So that was the idea why we created this 5 categorical variable. So this is the distribution of the regions across Chicago. So you'll see the TNC deficit region is around outer regions. If you look at the balanced region, the gray areas are typically in the downtown region. So this is where we initially expected downtown will have actually surplus, but we did not see that. We actually see that downtown regions, the demand is actually balancing with the overall demand. What we find is high TNC surplus routes are found along large transit routes. That is where we are seeing a high surplus for TNC. So what we are seeing is people are taking TNC to get to the transit station more and then using transit. So it's actually a good thing that we're seeing. There are some locations which are in deficit. These are the peripheral regions which usually are lower income neighborhoods. And these are located, these surplus locations are located around the route. So here you have the blue lines are the metro transit route, and CDL is a metro line that exists in, so these yellow lines are here. You will see a lot of red pockets of census tracts around the metro route, route L. So what we wanted to do was, okay, now we built the metric, we identified where each of these census tracts are. Now we wanted to understand, okay, what are the characteristics of these census tracts that drive them to one of these 5 categories. Okay? So for that, we looked at different categories of independent variables. We looked at socio-demographics, land use and built environment, transportation, infrastructure. So again, this theme, whenever you're developing a model, you would want to make sure you have a detailed set of attributes that you're considering. Usually, if you're looking at demand, you want the social attributes because you want to see what is the employment, what are ethnicity distributions, age distributions, vehicle ownership, income indicators of any form. Okay, whatever data is available in this report, that's something that is important. More and more focus is being given to land use and built environment attributes, where we are looking at, if you're looking at census tracts, you want to look at what is there in terms of in that census tract. So it could be what is the residential area, commercial area, institutional area, industrial area. All of these need to be considered. You also called a land use mix. This is a kind of entropy variable as a function of different land use types. Then we also need to look at transportation infrastructure attributes. Right? So frequency of L trains, number of metro trains, and different variables. So here, DB stations are the bike share stations in Chicago. Okay, that's a company that runs bike share there. We also look at infrastructure, walking, street length and side length of sidewalk. Again, I know some of these variables are harder to collect in the Indian setting, but whatever is available can be considered going forward. So here we were looking at how some of these variables change as a function category. So what we're looking at is percentage employed. So you see that if you have high rate of employment in that census tract, you will see that it's most likely to be balanced. Okay, so because there is movement in and out and people use normal travel and other things. If you look at this one, if you have a large portion of non-Caucasian population in high TNC deficit zones, you'll see 40% is the share of non-Caucasian population. So what we are seeing here is TNCs are underserving minority communities in the region. But similarly, if you look at age 65, again we see that people with high see, locations with high percentage of seniors usually fall in the deficit. So basically, again, they don't have familiarity with using technology, also are not comfortable with somebody else driving, so probably they are underserved. If you look at income, again, you'll see in high income, the chance of the PMC deficit zones have very little high income. What that tells you is usually the opposite is happening. It happens in low income communities. So this is again the 5 categories that we created allows us to see these better than using a single score. If we had a single score, we won't easily be able to capture these differences across the attributes. That's why we are looking at the category. Look at vehicle ownership, you'll see that if you have high proportion of zero vehicles, it's not surprising that you will have a lot more PMC surplus. So these are locations where there's a lot of transportation demand, but people don't want to use their personal vehicle. So they are relying on either public transit or TNC. So those are census tracts where you'll have high. So you'll see that they are less likely to be in the TNC deficits without vehicles. The last one is 2 or more vehicles. Again, this is what we're talking about in the beginning. So if you have 2 or more vehicles, if you have a large proportion of 2 or more vehicles, you don't need TNC. You already own multiple cars in your household. So this happens to result in a high TNC. This is actually a desirable thing, right? If people already have infrastructure to travel, you don't need to add additional infrastructure for them. So this is not a negative thing in this context. Again, we also look at density. If you look at density, this is one of the aspects that we talked about where if you have high density of stations, they are likely to fall in the TNC surplus. Again, this is also reinforcing the fact that surplus is likely to happen when you have metro station. Same thing with the metro service here. Again, similar aspects are found even with bike. If there is good bike share systems, so this kind of reflects high activity maybe of tourists and also discretionary activity in these locations. And then people are using a lot more TNC than in other locations. The last one is sidewalk density. Again, there are some differences, but not significant here. You'll see that with higher sidewalk density, they're more likely to the 2 categories, which is the TNC surplus. Okay. So now I'll quickly talk about the model that we developed. So again, these relationships are all nice to show, but there is no statistical significance associated with it and we don't know which of these dominates the others because it's all univariate relationship. I'm looking at relationship with A versus B, C, D, E all separately. But what is important is we want to look at when all of them act together, which of them actually means. Okay, so that's why we develop models because one-on-one relationships do not reflect any causality. They are just correlations. We're just showing correlations. We want to capture a little bit more than. So we have the 5 category variable. I'm using that as the dependent variable, and because we have 5 categories and the variable is ordered, right? We're going from very high surplus to very high deficit. There is a natural ordering of the variable, so we employ an ordered response model structure. Okay. Again, I will talk about these models in detail when we're doing the methods here. I just want to quickly show these things. So we create two. So this is how the model system works. So we create 5 categories. The propensity is captured by the blue curve. That is made a function of different independent variables. So that's what I'm doing here. The YQ star. This is the propensity variable. Epsilon Q is the what gives this normal shape or logit shape for the curve. The thresholds. So usually, traditionally ordered logit models only focus on the propensity. So the curve can move to the right or left, and the probability changes. If the curve moves to the right, probability for this alternative increases. Probability for this alternative reduces because that's the probability. The whole probability has to add up to 1. That is how we model an ordered response model. But in this model, what we are doing is we're also allowing for the lines to move for each individual. So depending on the particular characteristics of the census tract, the line itself can move. So we have 4 degrees of freedom. The curve can move, and 3 of the lines. There are 5 alternatives. You can only get 4 factors. So one has to be the base. So you can capture 4 differences. So you can either remove one line and three of these thresholds. Okay. Again, don't worry about the details. I'll go over that in detail because I want to start from scratch. We'll discuss that. Here, I'm just trying to show quickly. Again, this is the model structure. So we developed the model. We estimated a generalized order logic model. You can see clearly that the log likelihood is better. So closer to 0 is better. We also did a mixed logic model, mixed generalized order logic model, but it did not improve the Bayesian BIC metric. So we used the. Okay. So here what we are showing are the results of the model. As I said, we'll talk about the math in future sessions. Here I just want to show you some things that we're doing. Here you can see as proportion of population with age increases, the chance that they become high deficit increases. Right? We're modeling 0 is surplus, 4 is high deficit. So we're going from high surplus to high deficit. So a positive value here indicates as propensity increases, proportion of population with age greater than 65 increases, more likely to be deficit. Low income, they use. Again, if you see proportion of Latin and Hispanic population, African, so this threshold, this threshold is moving to the right, to the left, sorry, to the left. So what that means is this area will increase, right? If I move this line, the area available for the high deficit under the curve increases. So the probability of this alternative increases. If I move this to the right, the area available for the fifth alternative goes down. Okay, so that's why by moving this to the left, so that's what is happening when you have minority communities. What we're seeing here is that again, low income census tracts also the curve shift to the right. Proportion of high households, 2 or more vehicles. So here we are seeing the effect that if you have 2 or more vehicles, you are likely to be in high deficit. Okay. So you can interpret if you have high employment, you are likely to be in surplus because there is demand for TNC. We also looked at other things as you go away from CBD. So if you are closer to the central business district to Chicago, you will have more balanced structure. The further away you go, it goes towards deficit. We also identified trends that we expected for trains. So if you have L train, you see reduction in high deficit census tracts. If you have bus stops and DV stations, they can increase deficit. So what we're noticing is there's some interplay between metros and other public transit. So this was not what we found if you looked at the univariate data. But if you look at the multivariate data when we're developing this model, you will see that the bus stops are actually creating deficit locations. Okay? Because so people are using TNCs to connect to metros, but not to the bus transit system as such. Okay? These are city of Chicago has 4 spatial locations. We divided the city into 4 pieces. These are like fixed effects. We're just trying to capture factors specific to each part, central, north, west, or south, to reflect differences across TNC usage. So if just to give an example, if network's distance from CBD increases, the curve moves to the right. So what you will see is when that happens, the area of this alternative increases substantially. Okay. Now, another variable that we found for the same variable, not only does the curve move right, the threshold also moves to the left. So this even further increases the area allocated to alternatives 4 and 5. Okay, so that is the additional freedom that we get by using a generalized order. If you only use an ordered logic model, only the curve can move to the right or the left. But that does not allow for this nonlinear interaction where if only the threshold moves, that changes the probability. It gives you additional flexibility to modify the probability for the model. Yes, that's the reason that we use this. Yeah, I'll talk about this. So we can also do an elasticity analysis because the variable impacts are not easy to predict. So if you're using linear regression, if the coefficient is 5, that tells you that if my x increases by 1, my y increases by 5. That's the interpretation of the coefficient. It's not as straightforward when you have a generalized order response model because we are tying to something non-linear. So for that reason, you need to create a computer protocol either marginal effects or elasticity effect to clearly understand what is happening when you change one of the variables. So that's what we're doing here. For example, here, if you look at low income tracts, if you increase low income tracts, what will happen is you'll end up with more locations in the high deficit, which again makes sense. We know this from the coefficient, but we are just showing you the magnitude of it. Same thing with proportion of households with 2 or more vehicles. If you have more households with 2 or more vehicles, the likelihood that that tract will turn into a high deficit increases. So what we did was we changed all of these 10%. All of these values were changed at the same percentage to compare and see which has more impact and which has less impact. So you see that vehicles have a large impact. Income also has a large impact. Okay, ethnicity has some impact, slightly smaller, but still reasonably. So again, here what we're doing is we're trying to come up with a metric that we can look at in the context of overall transportation demand. We developed the metric, and we also explored how it relates to different independent variables. Then we developed the model, and now the model that is developed can be utilized to look at different pockets, spatial pockets in urban regions where there are problems. Okay, so we could clearly see that TNC usage is substantially influenced based on income, vehicle ownership, age, and ethnicity. Okay, so that's the main. Any questions?
Can you please repeat the slide 32 and 33?
So what we have here is, if you have a model for 5 alternatives, this is how the curve would look like. So what I'm doing here is the network distance variable has a positive impact on the propensity. So what that means is your curve shifts to the right. So when the curve doesn't shift to the right, this is a normal distribution or a logistic distribution curve. So this gives you the probability for this alternative. So if you add the area under the curve up to this point, you get probability for this category. If you want this category, you add the area up to here and subtract this. Okay, so this directly represents, so the area between these two lines gives you the probability for each of these alternatives. Is that clear? Okay, so we have 5 alternatives. So now, if I want the probability for this alternative, all I have to do is capture the area under this. So to do that, I'll take 1 because it's going up to infinity. So 1 minus all of this would give me the area of this. Okay, saying is when distance from CBD increases, my propensity increases, which means this will shift to the right. Okay, so now this is no longer the curve, this is the new curve. What will happen to the probability of this alternative now? What can you see? You can see that you have new area, right? So the area under the curve is now, when you compute it, it will be large. So you can clearly see that the probability for the first alternative goes down and the probability for the last alternative goes up. Clear? I can't say anything about the middle. Okay, unfortunately, because it's a non-linear system, it is not easy to say what happens to 2, 3. We need elasticity and marginal effects for that. But 1 and 5, I can clearly. Okay with that? Okay. Now, this is what would happen if you have a simple ordered logic model. In an ordered logic model, it's like tying a string to this curve and pulling it forward or backwards. Okay? That is only 1 degree of freedom. It moves left or right. Okay? Or left, right. Okay? So now, in a generalized ordered logic model, I have more strings to play with. What I can do is I can pull or tug on these thresholds. So that's what I'm showing in the next slide. So this threshold, because network distance increases, the threshold keeps shifting to the left. Okay. Now what happens because of this? So we have 2 effects, right? One, we move to the right, so this area increased. Now when I move this to the left, what happens to the probability for this alternative? It should increase, right? Because now suddenly the area is not this, but this, right? So the probability for this alternative increases, and potentially this also will increase because this threshold is tied to this. It could move. Okay. So what we are showing here is 2 ways of increasing the probability. Now, if you pull the curve like this, I mess up everything. I modify everything. Right? When I pull on the curve, I change this probability, I change this probability, I change this probability, and this probability. Okay. But if I only pull on this line, I don't change anything this side. Or I should say I don't change anything for these two. So what I'm saying is a variable can only affect alternatives 4 and 5. It does not affect 1 and 2. That is not possible in a simple ordered logic model. In a simple ordered logic model, if a variable changes, it affects all 5 alternatives. But in a generalized ordered logic model, by focusing on the threshold, I can create flexibility to say only 4th and 5th alternatives change, or only 3rd, 4th, and 5th alternatives change. So, the example I'm giving you here, 1 and 2 don't change. 3 changes, obviously, because the threshold is moved this way. So 4 and 5 also will change. So this is additional flexibility. Again, for people who use models, multinomial logic can do that. Multinomial logic can actually capture effect specific to any alternative. And this is used as the biggest drawback of ordered logic model. They say ordered logic models apply to all alternatives. If you do the thresholds correctly, it will do. Generalized ordered logic models are perfect equivalents to multinomial logic models for ordered variables. In fact, I work to show that if you have an ordered variable, use the generalized ordered logic model. It will perform, if not better, at least as good as ML. And we have shown in all our examples and all our case studies, it definitely outperforms ML. But still, there is a lot of hesitation because ML is easily available in software, so people use that more. But we think generalized ordered logic models are superior to multinomial logic models for ordered variables. Again, if you have an unordered variable, yeah, we can't use generalized order, so it doesn't work. But when you have a specific data set where your variable is ordered, please use generalized ordered logic models. They will do a better job.
We are applying logic because the variable is ordered or it doesn't follow normal, not continuous.
Yeah.
So distributed logic. So when we apply log, actually the nonlinear function is translated linearly. That is what the purpose of logarithm is. Okay, translate the exponential function to a linear function.
No,
so are we again and
so I'm not really for anything. Okay, the logistic distribution is simply how my error is distributed. Okay, so I am saying yq star is called the latent variable. So nobody observes yq star. We don't know what yq star is. So this is an unobserved variable. Okay, the only way I have some information is on the actual category. Okay, so yq is what we observe. It is 0, 1, 2, 3. If I take a log of that, I get log 0, log. That's not very useful, right? It's not like you have a continuous value, we're taking the log and running the model. No. Okay, we just have a discrete variable. We have 5 categories, 0, 1, 2, 4, or whatever you call it, 1 to 5, however you want to call it. And if what we are hypothesizing here is if the probability with the error term, because I don't observe it, is less than the first threshold, you stay in this category. Okay, if it is between this and this, again, I will talk about detailed order response. I'll get it. We'll talk about it in detail because I want to start with linear regression and go. So this is just a case study, so we'll get to it. Okay. So again, I'll do the elasticity. So let's look at one way. Okay. So this is proportion of population with age between 15 and 20. Okay. What I'm doing here is now I go into my independent variable. So I have this variable. I change this proportion by 10%. I artificially increase. So let's say it's 2% right now. I make it 2.2. If it's 5, I make it 5.5. Okay. So I create and then I happens to the probabilities and look at the change. So what I noticed is if I increase this population by 10%, these two categories do not change. This category reduces by 1.5%. Okay, this category increases by 1%. That is the interpretation. So for a 10% change in the independent variable, is the percentage change in probability for any of the alternatives. That's what I'm showing here. So for example, based on that, you can see that if you increase 2 or more vehicle households by 10%, you'll reduce surplus by 9%. So that's the interpretation. So in my group, we usually do elasticity than marginal effects, because in marginal effects are supposed to be for a small change. It's hard to interpret what is a small change. We don't know. So here we define the change. We say it is 10% change, and then show the elasticity. That kind of gives. It's not easy, right? For example, I can't really change the household's ownership of two vehicles by 10% very easily, but just to reflect on, okay, if that changes, what happens? That way, we are normalizing all these elasticities for the same percentage change. So they compare, oh, this is 1%, this is 9%, so it means this variable is more important than this variable because it has a more larger change. Okay. Any other? So again, the idea of the case study was simply to show how we can create a metric, and once you create a metric, how you can analyze it and see what variables are. So we will start looking at the second module now. So with that, I finished the first module. So again, the first set of slides was on providing an introduction. Now what I want to do is I want to start looking at what is public transport data, how we can use that, and so on. So I'll talk about passenger data, and also look at what do we want to analyze. How can we analyze that? That was what we'll talk about. So, different components of public transit data. Again, all of you will be aware of some of these elements anyway, so I will talk quickly about them. So, passenger data is one of the most important. Right? So, if you want to model public transit system, you want to look at ridership, you want to look at for different origin and destination. But there are other components of data. Right? So, there is data on vehicles. So you can look at what are the fleet compositions, how many vehicles are there. The transit agencies also have to decide on some of these numbers, how many buses to own, what kind of fleet mix. I mean, are they going to have all of them diesel, how much of them electric, what capacity of those, and how are they utilized. So if you look at a vehicle, you're running a bus, and how often is it full? How often is it half? And so on and so forth. So all of these are also important data. Then you also have what are travel information data, right? So different agencies are investing a lot of resources in providing this information readily to passengers, right? So if you have an app for the local agency and you can see where the bus is, or if you at least have some information on when the next bus is arriving, if you're waiting for a bus, and if you know the bus is arriving in 3 minutes, the 3 minutes will fly much faster. If you don't know when the bus is arriving, wait exactly the same 3 minutes. Because of the uncertainty, it will feel long. Okay, so again, agencies are recognizing value to providing information. I mean, even if it says you have to wait 15 minutes, knowing that it comes in 15 minutes makes your life so much easier. You know you can plan. So at university, the transit system is run in a way that they actually provide when a bus is coming to an apartment. So I know students who just start walking down when the bus. Right? So it gives them that, and they don't waste their time waiting in the bus stop. They actually can do or get a plane, whatever it is. They can come down right at the time when they need to get onto the bus. So that information is easier for people. And also if there are disruptions, right? So sometimes the bus can have a breakdown. Knowing that and not having to wait 1 hour to figure that out is very helpful. So there is a lot of work that goes into providing that, and there are also GTFS routes where geocoded routes are provided for all transit, and times are you can use that to figure out when the bus arrived at each stop along a route, for instance, and then use that to model how many times the bus is arriving on time, it's late, and so there are all of these elements that can be looked at from travel information. Then there's also the financial, right? So each time there's a ticket that is purchased, there's revenue generated, there's expenses associated with how the lines are managed, there is employees who are working, their salaries and so on. So that could be one component of financial data that can be looked at. There's also the workforce, right? So there are how many employees do you need to own? In some cases, they're outsourced to private companies. They manage the fleet, they manage some of these aspects. Again, salaries become a big component because usually public transit systems are, again, not in all cases, but usually publicly owned. So there are always challenges with respect to funding and salary negotiations, and if you have unions, there are stricter discussions that happen. So again, there is a lot of data that can be used in the realm of public transit. Okay, we won't be able to. I think years you want to cover all of these data sets and so on. So what we'll do is I will focus on the passenger data. Okay, we're talking about mainly about that, and we'll refer to other elements as necessary. But I'll focus on the detailed passenger data analysis that we can do as part of this. Yeah. Okay. So again, there are different components to passenger data. One of that is ridership. Obviously, the numbers you can look at ridership at different resolutions. Look at ridership at a stop level. So if you're a station or a bus station, how many people get on at each stop can be variable that we analyze. Some people might say, okay, I'm not really interested in every stop level. All I care about is how many people are using this bus route. So that would be the route level. But there could be higher level policymakers don't really care about even each route. Right? They focus on how are the ridership number and system level, and how are they changing by different time. So again, the ridership data is very complex in the sense that not a single number. That number can be passed at different resolutions. Right? So if you think about the city bus system in any major city, right? There are the fares are also available by zones, right? So usually they are not measured. Revenue is not measured at a stop level because there could be 6 stops from where you can get on and pay the same fare to go to your destination, right? Because you cannot change the fare for every stop. There are multiple stops within each region where you're paying the same fare. Okay, so in that case, the agency doesn't care which stop you're getting. All it cares about is which region you're getting, right? So sometimes they don't even collect data at the stop level. They're not collecting how many people are getting on board at every stop. They're only collecting region. There are 5 regions for us. Region 1 to region 5 is 35 rupees. Region 2 to region 5 is 25 rupees. So they have this fare system where every region to region they have different price fixed. So all they care about is flows between these 5 regions. They might just collect that a matrix of 5 by 5. But they don't really care about which stop people are getting on because it doesn't matter monetarily. But it might be important for us to understand what happens at each stop because if you want to provide a stop station, bus station or a location where people can stand, you need to know how many people are using it because you cannot do that at every stop. You don't have the money to do it or space even to build that infrastructure at every stop. So there are challenges in how data is collected and how we want to use it as planners and engineers for improving public transport. Okay, so there are some challenges like that we need to consider. And ridership changes by time. In the morning peak, afternoon peak, evening peak. So again, that is something to look at. Weekdays versus weekends, there are a lot of differences. So again, if data is collected at different resolutions. So for example, if somebody is willing to give you data for every hour, then you can characterize that into any classification. But all they have is day of data. They are only collecting daily numbers. So they're not tabulating data on an hourly basis or in continuous time. It becomes more challenging because then you have to reflect everything. The impact of employment is varying by time, but we cannot capture. All you can do if you have only daily numbers is put that as the independent variable and focus on what is the overall employment at daily basis. So it gets tricky depending on how transit agencies collect it. Ideally, we would like to capture data at the highest resolution possible. So if you have an opportunity to collect data or request data, always start with, okay, I want it in continuous time at as fine spatial resolution. If they say we don't do that, you can always think about ways of aggregating that. But your requirement or effort should go into collecting data in as small a time scale as possible and as small a spatial resolution as possible. Okay? Because once you have that, you can do anything. You can always go from bottom to the top. You can never go. There are ways, there are approaches that can be used to go from top to the bottom, but those are all models. They are not real data. Right? So what you're getting are estimates. It's not real. So we have to be careful. Other data that is important for passengers is we need to understand the demographics and socioeconomic data. So income categories. If you're looking at any public transit system, you can define what's called a catchment area, where people from the region that are going to use that service could be a bus. So catchment areas for bus stops will be smaller, could be slightly larger for metros, and especially if you have good first mile, last mile integration. But you understand who are the users of the system. Okay, for that we need the demographic and social. And the third thing that is important is we need to understand the travel pattern, because again, they govern who uses public transit or any other. So if you don't know how many people are traveling from different parts of the city to other parts of the city, we cannot design our systems to manage demand effectively. Okay, because this is what gives us that information to see, okay, now there are so many thousands of people going from A to B using car. What would it take for them to shift to public transit? How can we do that? So, but even for that, we need travel patterns. Then the last element is individual level data. So the first three dimensions are what I would call system level data, where we are capturing data from the perspective of our transit system. But individual data is where we're trying to focus on each rider. We're trying to figure out, okay, how many times does this person use public transit or other modes? What is the cost that they're paying? What purposes that are, so this would be what you call a market survey kind of analysis, where you can develop, okay, how do we convert people who are currently driving to public transport, focusing on individual level. Okay, again, the analysis for the ridership data will be different than individual level data, because again, the objectives are different. But this is what defines some of the challenges in how we model and analyze. Any questions? If I am modeling stop level ridership, let's say I'm building a ridership model at the stop level, all I care about is how many people are coming on the metro or on the bus at that stop. But I'm not looking at each, because once I'm modeling the count of people, I'm not modeling each. Right? Yeah, if there are 5 people, but I cannot, there are ways how we can capture the actions of those 5 individuals. Is to group them as 5. It's a count. We're looking at that. But individual, I'm actually looking at what is the age, that level of detail. You cannot capture that level of detail in the registry.
So in this software, kind of data combined they should be from one.
Yes. So what we look for, I'll talk about that. Well, what we look for is we use this approach. We draw a buffer in GIS, and what is the population with how much? Right? As population increases, hopefully, right? So values variables you use, and also look for what is the density of transportation network in that region. Look for public transit. So all of these. So I'll give you. So we look at variables from different kinds of categories, and then sometimes data is not available to do a buffer. Then what you will do is, okay, maybe you have a census tract or some kind of larger aggregation of zones. You use that as much as possible. So I want to show some numbers here of some data trends that are happening. So I selected San Francisco because San Francisco area is an agency that provides data openly. So for now I'm just showing you. So this is ridership data So for different modes. So here are the different modes that exist in the region. So you have bus, which is predominantly the majority mode. Here you see commuter rail is the large one, heavy rail is this one, light rail is this one, and there are other modes. And ferry, ferry is very small. So what you will notice the moment you see this chart, the impact of COVID comes apparent, and you see the drop. So we were talking about bus numbers ridership has been declining. Okay, you notice that it has been declining, and then what happened after COVID? So 2021, 2020. So it has rebounded, but not anywhere close to what it was. We talked about 900,000, which is again going down, but it has not come. And it was a bright spot. Heavy rail was increasing over time. You see that in 1991 it was around 250,000. It actually crossed 400,000 in 2018, 2019, but then it dropped precipitously after COVID, and not even at. Okay, this is show more numbers. What we're seeing is COVID kind of, especially in the US, has been a big disruptor for public transit system, and they're finding it hard to recover from that shock. People have found, hey, some of them are working from home, they found so it's a big change. So here there are different systems, subsystems within the San Francisco region. This is the bus system. So you see it's called Muni. You'll see average number of riders in billions. Again, this is the different years. We also 4 and 2025. Okay, this is 21. You'll see the drop. Biggest drop happened in 2020. After 2021, again things are improving, but nowhere close to the top. But it's getting better. Okay, so you see that it was around 0.7 million. It's now come back to 0.5 million or 0.4 and half, 0.5 and so on. So hopefully with time things will improve. But the target they had for 2024 was 410. You can see in some months it crossed, and in some months it was close to lower than that. But usually it crossed. The target of 410,000 trips was met in 2020. So there is recovery happening, but slow recovery in this. This is another system within San Fran. You'll see the bus and transit. Again, this is yearly data. Okay, so over the years, ridership has been going down. We're at 13 million here. You'll see it goes down to 10 million even by 2019. But 2020 substantially from 10, it actually became half. But what is good to see is that it is recovering reasonably. So we are close to the 10 million they had in 2019, about 8.5 million. So hopefully it will recover. This is, they have Bay Area has the Bay Area Rapid Transit. It's another part of their train system. Okay, you'll see the same thing here. 2019, very high numbers. 2020, very high numbers up to March. That's when COVID hit. From March, it kind of becomes very rounding kind of numbers. Same for 2021. We still, even in 2024 and 2025, we're not even halfway to what it was in 2019 and 2020. Okay, so again, substantial challenges. These are all long distance commuters that now, because in Bay Area, because of the technology, there was significantly more working from home. Even now, people are doing hybrid work. There are some policies that are being implemented where people are required to come to work. So this should change in the future. But so again, these data sets would be the starting points for any public transit analysis. If you want to do ridership analysis, you're starting at looking at. Okay, now these are very aggregate. Like I'm giving you one number per month or one number per year. This is not what you want to model, but sometimes you want to go into more deeper numbers because this is I'm giving you one number for the entire system. That's not what you want to use. You want to use more detailed data, but this is just to give you an idea of how the data can be provided. So you'll see different agencies collecting data different. You'll see this is, for example, the monthly data profile here. This is only year. This one again is monthly and by different years. So different agencies will compile this information in different things. Now, with smart ticketing systems in place, data collection is easier because as soon as somebody puts in their metro card or so on, you can actually track their origin and destination if they swipe both sides. In some state transit agencies, you only swipe when you're getting it. You don't swipe when you're getting down because the prices are fixed that way. So in that case, you only get origin data. You don't get where people are getting them. For that, you might have to collect that. So based on the specific system study, there will be specific challenges for the system in collecting it. Okay, so sometimes there is no smart data collection. There's a conductor who punches the holes and gives you tickets. That is very hard to compile, right? Because they go back and report, they provide some numbers, but I'm not sure that's easy to collect for researchers to view, and how reliable it is, mistakes, a lot of mistakes that can happen. And then there's also this challenge of they are not based on the stop, they're based on the reach. So you get in 23 or stop 28, they don't, it's the same price. So there's no way for you to know where they got in. So there are some challenges. So this is an example of the ridership. So here is an example of demographic. So what they did is they collect demographic data by conducting survey of transit users. Okay, so they're going to ask people as you're on the bus or on the metro system, they give you a survey and they ask you where do you live, what is the household size. So again, these are summary. I'm only showing the summary characteristics from their surveys. So for them, these are the important characteristics. For example, average age of respondents is 40, average household income is so on and so forth, and they are able to get some information. So this can be utilized to understand who are the writers. Okay, so they have good proportion of English speakers. You can see there are many languages. San Francisco Bay Area, so there are immigrants from everywhere. Similar data can be collected for every system. You see, look at the income numbers. The last line is something I want. So Muni is used by individuals with an average income of about 90,000. If you look at San Francisco, 53,000. Look at Bart, 105. So this kind of shows you the transit system. Okay, so it is used by reasonably high. Beginning in San Francisco, 91,000 is not very high here. San is used by low-income individuals mainly, or lower. Bart is individuals high older, majority living in Bay. Okay, so these are the numbers that we see. So this is how demographic data will be available. So, okay, so the data collection and compilation for ridership and demographics are different. When I collect ridership data, I'm not, if I keep asking them what is your age, gender, nobody's going to give you different, right? So that is collected differently than how you're collecting ridership. So you need to figure out to use both efficiently. Okay, so this would be collected in a one-time survey, maybe once a year. If you have a good agency, they do it once or twice in a 5-year window. It's very hard to collect the data. It's expensive. In San Francisco, they're collecting it once or twice every 2 years. So which is a very good data collection. But now, the other thing that we wanted to talk about was travel patterns. So here I'm just showing you an example of travel pattern data. I thought they had a very nice presentation in San Francisco. Let me data set illustration that they're showing for how San Francisco trip patterns exist. So here you can select. So these are the main regions. So you see the regions in the San Francisco Bay Area here. Okay. And they are showing you, okay, obviously this is everything. If I select something here, they'll show you travel from that. So, right, so they're looking at Marina Heights here. I selected that. So the wider is the band, the more is the trip. Right? So if you look at this one, so more people are going. So all that there are 285,000 trips going from there. So 4,000. Then down. That so the thinner the band, the fewer is the trip. So it's a very nice way of showing how the demand moves. Again, this is hopefully they got this from a travel demand model and they're aggregating it in this fashion. So you can look at anything you want. So it's a very nice way of data illustration showing where are, so here we are focusing on South Bay. From South Bay, where are the trips going to, which parts of the city they're going to. Okay. So again, this would be a good mechanism. Even if you're just showing your transit data, when you're doing academic papers, it's always good to show the data first. When you're the first section of your data description, again, people are getting tired of looking at tables and average and means and distribution. So again, look for newer ways of presenting the same information because it's more catchy to see something like this than if I just gave you a table of all the ridership, all the flows between A and B. And it's not easy to show them because once you have this 11 or 12 locations, it becomes a table with 144 cells and nobody's going to look at it. So again, I thought this was very nice. So, and you can also do some of these by purpose and mode of travel. Obviously, once you put walk or bike, the numbers drop substantially. Right? They're not that many. This is transit. So you'll see from South Bay, people mainly go to downtown, right? So that's the picture you can see in terms of public transit. So everything else is small. Again, you can also look at Uber and Lyft. You can see a good number to downtown, some numbers to other locations. So this would be the main mode of transportation. Everywhere it's using. Okay, so again, there's also numbers by 2050. You want to look at change. Okay. It's a very well developed website. You can play around. I have the link if you want to, if you're interested in the slides that is there. So you can look at that. So I thought this was a very nice way of showing some of these relationships. And if you don't select anything, yeah, not here. So this kind of gives you overall trip patterns by trip purpose in the region purpose. Any question? So the last dimension of data that we talked about was the individual data. So this is where we are looking at specific individuals and trying to understand characteristics of. This is also different from the demographic data that was selected. But here we are asking more questions about the individual. We are asking how often do you use the MUI system? So we are asking, so 40% of the people use it 6 to 7 days a week. And then there is a few people who use occasionally, so these are what we call occasionally. So again, we might want to understand who are the people who are using it very often, who are the people who are using it. Again, this would be something that we analyze. And you can ask more information, asking, okay, what changes would get you to use transit mode? So again, this is a very, it's a loaded question because obviously this doesn't necessarily mean that you make those changes and people will use transit mode. It's just what they would like to see. So again, most common comments would be this: they want more frequent service. The current frequency is not enough. They're asking for more reliable, so they don't want the delays that are happening. And again, inner vehicle slower pace. So again, these are subjective questions which are useful to understand, but they're not going to give you quantitative response. So what I mean by that is, even if you increase frequency, we cannot tell what will be the increase in ridership because of it, right? Because this information is not translatable into quantitative numbers in that fashion. So we need to be careful in using this. A more rigorous approach would be to build stated preference questionnaires where you provide them the new frequency new fare, and then see what is the frequency at which they will adapt this mode and so on. So these are different things that you do. Okay. We did. So the next part, what I want to focus on is we looked at the 4 dimensions. So I don't think the Mentimeter thing is working well, so I'll stop here. So I wanted to ask some questions on, okay, now given the different dimensions of data we looked at, okay, so what do you think are dimensions that we should study in public transport? What are your thoughts? What would be the ideal ridership variant? So let's say you have infinite resources to collect data. So what would you collect and what would you? Louder,
Individual.
individual ridership, okay?
Because it will help us to overcome the aggregation errors and
Okay.
unit level factor of the
So how will you collect individual ridership? How many people will you use?
this population.
So would your idea be to collect data from for each individual or sample? Obviously, you can sample. Would that be your approach, or would it be more beneficial to collect data at the stations or at the? Okay. So again, depending on what question you are trying to answer, yes, those are valid approaches. You can look at that. Now, if I am a transit agency and I'm trying to figure out how my ridership happens, so I only control what is going on in my system, right? So the easiest way would be I look at my ridership data from the system, right? So and then supplement that with some of the TSDs that are available, other data that you can look at. So you start looking at demand. Now, when you're trying to analyze, you want to look at interactions. What I mean by interactions is how is ridership changing over time, first of all, because populations changes, patterns are changing. Then also, we want to look at how different changes to the system are influencing ridership. Right? So usually, yes, we are running a transit line. It's not like it's static. If you change the route sometimes, you change the stop, you change the schedule. So you want to understand the effect of these variables on ridership. Okay? So those are some of the dimensions that we want to look at. Also, for example, in Hyderabad, right? Metro system is relatively new. I wouldn't say it's new anymore, but it's so now what is the impact of that as it stabilizes on bus transit? Because is it increasing bus transit or is it competing? And if there is a coordinated integration efforts made, again, Metro is bus transit, a different agency, so it's not necessary that the schedules are coordinated. What I mean by that is ideally what you would want is a bus arriving at a metro stop right before or right after the metro comes. Right? So that way people who are going to get onto the metro can come there and who will leave can also go through. So that way it's a more integrated system. So more people will find that seamless connectivity and use. Now, even to understand that both agencies have to collaborate, but first thing is look at data on what is the so before ridership, what was the before metro ridership, what was the bus ridership? What happened after the starting of the metro system? Is it increasing bus ridership or is it reducing? So the impact might not be constant across the entire city. Right? There could be locations where they compete. There could be locations where they complement each other, and there could be locations where there is no impact. Right? So again, you cannot use a one-size-fits-all approach to all of them. You'll have to do this carefully and look at some of these aspects. So let me go through. One more thing to look at when you're talking about ridership is there are two components to ridership. Right? People get on the bus or on the metro or whatever, and also get down. So there is what's called boarding and alignment. Right? So both are important. So sometimes when people are modeling it, you can add them into one group and model the whole thing. Because it has implications for passenger minds, right? So if you know when a person gets on the bus, and if you know when that person is getting off, you can track the person miles on the transit system. Right? You need both origin and destination to figure it out. If you only know the origin, you know where people are getting on, but you don't know how many miles they're traveling on the public transit system. That is one metric that is important, and especially that if you want to do, we did some work on looking at the person emissions per capita on public transit, right? So a public transit bus, if it goes empty for a long time, it is actually not better than a car. You actually are emitting a lot of pollution when there's nobody. So one way to there are a lot of works assuming average occupancies and then using metrics to generate per capita emissions of public transit. But what we did was we built a micro simulation system. We were simulating boardings and alightings in real. So there's a bus, let's say bus number 100 goes from A to B, which is 20 kilometers long. And along the way, there are 100 stops. Okay? Wherever there is a stop with a person getting on, the bus stops. Otherwise, the bus doesn't stop. Okay? So, and it probably runs that 20-kilometer route 6 times in a day or 12 times in a day. So what we did was we predicted ridership at each stop in using micro simulation. So what I mean by that is the bus starts at 6 o'clock in the morning on stop 0. We will run a model, see how many riders will board the bus. That's it. So the simulation comes with 2. So we wait for the 2 people to board. So when the bus is idling, when people are boarding, the more people board, the more idling emissions come into the picture. Okay? So you can do a very high resolution emission, do a simulation of the system like this. So we did that for the entire system of Montreal, Canada, and then we were able to compute because we are simulating it. We know at any instant how many people are on the bus. We have a bus capacity. If the number of people boarding is more than that, so we have a continuous tracker of 3 people are on the bus now. Next stop, 1 person gets down, nobody gets on. Update that number, and we know the distance between the 2 stops. So we can keep track of the person. So there are 6 people on the bus, they went half a mile. So 3 miles. So we can keep track of the total person miles of people. So when we come and we are tracking the speed of the vehicle based on average speeds, and we were able to generate, my colleague emission side, she was able to generate estimates of emissions at a precise resolution based on the roadway segment where they're traveling, the slope and so on. So we were able to generate a very accurate system of person level emissions. So that would show which route. So some routes are very efficient, right? Because they have a lot of ridership, a lot of occupancy that happens, so they're very efficient. But then there will be some routes, so you can actually identify which routes are actually contributing to lower emissions, which routes are contributing to higher emissions. So you can figure out ways to change adding EVs. It might be better to add EVs to the less efficient ones, right? Because these are the systems where there is more pollution, less people are using. But if you have a diesel bus which is always occupied, maybe it's not as bad in terms of the emission. So again, our objective is not to decide on the policy. Our objective is to give mechanisms for policymakers to see where things are. So ridership can be liberated from that perspective. Another thing that we want to analyze is the impact of public transit. Right? So we are looking at providing this public transit system is to increase accessibility. So there are a lot of studies and research efforts looking at how many jobs can people reach using public transit. Can they reach groceries? Again, this is not a problem in majority of India. I think grocery stores are available in close proximity. But in the US, it's a very suburban kind of development. You will have no grocery stores for about 5 to 10 minutes. So if you don't own a car, it's not easy to walk. So there are what are called transit deserts. Transit deserts because people cannot go to groceries, people cannot go to public health, healthcare, and even other facilities are not available. Okay, so that is something that is very heavy. In the Indian context, it won't be from a desert perspective, but what we're trying to do is improve accessibility. Right? We still want to make sure more people have access to some of. So that is something to look at. And when you are looking at accessibility, another dimension that is important is how are these transit modes accessed. So, for example, in the US, if you have commuter rail, there's a lot of parking in the stations. People drive, park their car, and then take the train. Okay, so now because they're driving, there is an interesting problem that you can look at is people can go to a metro station or a commuter train station which is further away, which is more likely to have parking than a station close to home. If I'm leaving my home at 6 o'clock in the morning, I know I'll get parking. So then I'll go to the closest station. But if I'm leaving at 8 o'clock, maybe the small station's parking is filled. So I actually drive 5 miles and then take transit. So again, there is a question of how do I get to the train station? I can walk or I can take the bus. I can actually drive, and then which station is also a choice that some people will. So some of these analysis is also used. So this is an example of some data that the Chicago transit system provides. Again, just like the chart that I showed you, this is also something we can look at. They provide the ridership information. They provide on-time arrivals of buses if any delays are there. Again, these are good ways of presenting the information. If you're a transit agency, we look at these as the mechanisms to present, and also I think you can collect. You should be able to collect some data from this to use it to come up with some different metrics for them. And another important thing that we need to look at when you're looking at ridership is you cannot have a one size fits all. I just want to give an example based on what we did in Montreal. So there are 8,000 bus stops in the system for ridership. Okay, but you cannot have a single model for all of them. It's not always helpful to do that because there are some stops which have 8,000 boarding center units. Okay, but there are many stops which have zero. So you need to figure out a good way to characterize those. So that we can call them, cluster them into different groups. So here I can give you an example. So what we did was we did 3 clusters of stops. We looked at stops with low ridership. So this could be a bus stop in the residential neighborhood where maybe 3 or 4 people get on during the day, or up to maximum of 50 people. So what we have is there are stops with ridership less than 50. So these are the low demand stops where they're right next to homes, few people that get on. Then there are what are called medium sized stops where you have ridership anywhere from 50 to 50. This could be stops on collector roads or arterial roads where there is decent demand. And then there are high occupancy stops. So these could be transit centers or locations where multiple bus routes go through them and you have a lot of people use. The largest sample is in the low category. So most of the stops with very little demand, right? So you have about 3,500 in the low category, but in the high category you have fewer stops, but they contribute to the highest amount of ridership. So 18, 13 is the number. Okay? So are you fixing it at 11, 15 or 11, 13? Right.
So what may be other way of clustering those stops? Since this is in terms of realized, how about the clustering based on station, placement of the stops? Be it CBD or suburb or various.
Yes.
That can be one.
Yes.
The other can be like their proximity to transit stops. So, proximity to various kind of facilities.
You could do a multivariate clustering also. Right? So here we did this, but you could look at clustering based on land use characteristics, clustering based on location. Like you said, distance. So distance to CBD could be one way, right? So you could use. So if you're looking at clustering for different variables of that nature, I would like doing it by multiple variables, not just right. So you can do clustering based on attributes that you can decide are important. So it could be income of the stop, right? Stop. Yeah, you can do that. So you can use k-means clustering or any of those approaches to create that, and then you can use it. So here our focus was not on that, so we did not do, but that's a valid point. Yes.
Within the four terminal stations, access to the facility is almost they were already positioned in such a way they have some similarity
Okay.
for the four stations.
Yes.
And along with that, if the ridership is varying from medium to then only they consider the four stations together to do the interface.
Yes, you can do that. You can do, yeah. So if the total, so here because we have 8,000 stops, we cannot do a station stop specific model. But if you only have, let's say you're saying 4 and 7, you can actually do a model for each station, right? Because there are only 7 of them, right? So you can go more personally. Again, we could still do them. We still do them. You can start adding specific interaction variables for that station. So you can have population, but you can add population times station 1 as an additional column of it. So there is a common effect of population in all 7 stations, but there could be additional effect of population on station 1, station 2, station 3. So you can capture. So that way, even though you are doing a single model, you can provide custom estimates for each station. Okay, so
Here population, we are speaking about the metro.
catchment area variable, population, or just as an example, it could be highway or a number of trains. So each terminal might have different number of trains coming at different points, things like that. And then also what is around that station, right? Within half a mile or 1 mile or 1 kilometer. Each station will have different characteristics.
We can't combine this, like, then it can be individual analysis.
No, the variable will be the same for all 7, right? The name. So let's say I'm capturing, let's call it M1, number of jobs within 1 kilometer distance from the station, right? So for station 1, the number of jobs would be 3,000. So, but it still is. So my independent variable is M1. So I can come. Another challenge in this is you have only say, but you will have multiple days of data. The challenge here is you will have repetitions for the same station.
So for example, ordinary, by considering the, for example, the four terminal stations, there are only two variables for the station by considering first is the and the ridership. And ridership is going to taken certain limit, if it is in this direction, the station will be considered. And so we have clustered the station. And for that particular station, if we are considering about 10 variables, then can we club these four stations together?
No, you have to be careful. You have to be careful with combine. You can combine them. So there is an approach called pooled model development, where when you're developing the pooled model, I can develop specific to any observation, but do it jointly. There's a mechanism to do that. So you need to create what are called. So for every variable, let's say you have 3 variables. Just as an example, right? So let's say population, income, and ridership are the 3 variables. For each of these 3 columns of data, I can create multiple copies of it by multiplying with a dummy variable. So what I do is population times station 1. What that means is if it is for station 1, the population is multiplied with 1. Otherwise, I multiply with 0. So if you have a column of data, the first column there is population only. In the second column, I have population station 1. So that population variable is seen only for station and 0 elsewhere. Similarly, population station 2 will be 0 for station 1, population for station 2, 0 for everything else. So you can create, you have 10 stations, you can create 10 columns, 10 sets of columns like that. And you introduce one base, which is the variable, and you can introduce interactions. So that way, in a single model, you can actually capture impact. The reason this is useful, this is efficient, is because population might not be different for 6 stations. The effect of population. So if you do separate models, you get 6 coefficients. But if you do one base model and 5 interactions, and all 5 interactions are insignificant, you will recognize that population. So that analysis is easier. Separate models, you get share of population is, let's say, 3 in one, 3.5 in the other. You will say, you think they're different, but in reality, statistically, they're not different. Okay, so that's very good. We can talk about, if you have data, we can actually talk about how to do it. So other dimension that we can focus on is also system operation. So for example, there is focus on understanding travel times per route. So which are the routes? If you're a, this is a supply side problem, right? There's a demand side problem which is ridership. If you look at the supply side, you're making sure the infrastructure is enough or not. You want travel time reliability to be an important aspect. How much on-time arrivals are happening? What are the delays and so on? And then you also want to make sure there is analysis being conducted on understanding how much time are people waiting for the bus, right? And then much is the walk time in the people have. So these are things that something that might be looked at. Customer satisfaction, I think the perception survey is conducted to understand whether it is serving the needs of the people. So these are all elements that you can analyze. The last component I identified is societal impact, where you can look at how using it reduces private vehicle usage, hopefully reduces emissions, and so on. The role of public transit goes beyond just transporting people, right? So there is, if you look at, it changes the communities, right? Improving connections between communities. There is a tangible value of that. There is also positive improvements to property values in the transport. All of these are examples of locations where the property before the metro station or the station into existence, that region was not as prosperous. But once it comes in, new retail, new facilities, new schools to existence, and that change the land. So those are things that are important to measure. So we talked about the dimensions. I want to talk about how to analyze, right? So I want to model leadership. Usually it is modeled as boardings or lightings. So it could be stop level, it could be region level, and so on. So the variable is right? So if the ridership numbers can be large in some cases. So if you have those large numbers, if you only see 0 through 5, maybe you don't want to do linear regression, you want to do ordinal models. But if you see numbers going from 0 to 150, 200, and so on, you might use linear regression or count. We'll talk about. If you're modeling travel time, again, it's a continuous variable that requires linear regression. If you're looking at impact of transit and we're modeling property values, these are continuous numbers. Again, you can use what is called a hedonic regression model. But if you're looking at mode choice, station choice, and route choice, there we get into categorical way. Okay? In those cases, we will use discrete choice models such as multinomial logit, nested logit, and so on. If you're looking at customer satisfaction, this is something that is done routinely at different transit agencies. Let's say they go from customers are very happy, very good, good, fair, poor, very poor. So this is an example of an ordinary. From very positive to very negative. So it is more appropriate to use ordered response models. Yeah, okay. So basically what I'm doing with the we need to understand how linear regression models work, how categorical models work, how ordered response models work for understanding different facets of data. So in the next coming sessions, we'll talk about those models, and also I want to talk about some supplementary data. So I'll pause here, but we'll talk about the supplementary data also, and then move on. Okay, thank you.
building a kind of TNC stuff with the transit system. But basically, it is not exactly relevant to the transit alone. So even if it is the data which will be depends on some of the secondary or maybe some of the other categories of the data which can be relevant to analyze the public transit system. So that will be going to addressing here also. So this is the kind of the content coming up, like the data types and the data collection process. So apart from that, suppose if you have the kind of big data, how it can be analyzed and what are the sources of the big data, and some like few case studies are also exploring here. So basically, there are two different categories of the data generally we explore. So like we generally talking like endogenous data sources and the exogenous data sources. So mostly these endogenous data sources is not depending on the customer sides or like the respondent sides. It is generally available at some point of the time and it is updating frequent interval. Maybe the best example everybody knows that is the census data. Or like the Indian economy data. Like even if you look at the Indian economy data, so generally they collect at a frequent interval times and they will be updating. So this economy data is very, very important source for the when you are planning or making any kind of policy decisions relevant to the transportation system. So these data sources are openly accessible mostly. So we know that like the openly accessible of the even population data mostly are like GDP data. So then sometimes we need to collect some of the data systems, like we need to collect the specifically some zones data, then understand what sometimes the population is not accurately collected because it is a macro level scales, then it is very difficult to get some kind of micro level information. Suppose if you want to know the vehicle ownership data, maybe like specifically household size or like the household category income levels, then it's very difficult from the population data. So then we need to collect the specific to the zone area. Then I need to, okay, I have the population data, then I have the disaggregated micro level information, then I can easily compare. So what purpose we need to do this process? Mostly maybe the PG level or like the college level, you might be knowing you are already dealing the data. So why we need to do that actually? Like suppose I can't rely completely the data source as the endogenous cases. Like you have the population data. Can I make the model completely relying on the population data? You can't do that. So even if you want to do that aggregated level, still it is having some kind of missing information, or you don't get that what you want to exactly trying to capture it from like predicting corresponding to your models. So that's the reason. So I need to make that some kind of micro information from the survey data information, so like collecting of some topical like survey related information that will be collected again with respect to your openly access information. Then finally I will use the data for modeling purpose. So generally this will be updating on the regular basis of the intervals, then ensuring of the functionality and the reliable use of the data with respect to the output, respect to like the output perspective to the information what we have gathered and what we have in the system. So, but in the exogenous data sources, so it is the data sources which are the weather, like the traffic, social media, and the smartphone, or the survey data. These are the categories we have. Even if you want to collect the weather, so I need to keep a kind of weather station, then I need to collect the information. Though you have the weather information online sources really, that can be compared. So because suppose if I want to know the direction of the wind and the particular case of the system, time period, it is very difficult. Sometimes that particular station might be working or might not be working. So then I need to collect that particular information by using some weather stations. The same in the case of the traffic, social media, or the smartphone related data, or like cellular based data. So then most of this academic research often utilizes the different types of the fields of study data, and maybe we generally much rely on this survey data. Like we need to collect the data based on the surveys, then we need to make the sampling, then we need to correct the sample data, then we need to identify the final sample, then we generally process for the analysis. So now if you look at the survey data, so it is collected from the sample of the targeted audience. Now if you know that like the audience, the target is the target audience is corresponding to the objective what we said. The objective is to understand the public transit system, then my target audience will be public transit related passengers. You should not collect that just home interview surveys. Even if you collect the home interview survey, then you need to sample it how many number of corresponding to your home interview surveys, how many people are actually traveling by transit. Let us assume you collected a home interview surveys and no one is traveling, or maybe like very less number of samples are corresponding to the home interview survey relevant to the transit, then the data need to be questionable. The same way. The endogenous data generally need to be corrected, like which means that I have the population data. Let us assume that you need to want to estimate a population density. So I have the population densities are like populations on the entire city level, but I don't have the disaggregated level zone populations. So then I need to go to the zonal population system. So then I need to collect some information at the zonal level. So it might be not even the secondary, it might be relevant to the direct service sometimes. Or maybe like suppose if you want to know the household size specifically. So sometimes they may give in the entire city level household sizes in the population, but you don't get the household size of the zones. Generally, they don't provided the disaggregated level information in the population census. So that case, I need to make that okay because I need to make my study relevant to the zonal level. So then corresponding to micro or like the disaggregated cases, then I need to collect that okay, corresponding to this zone, at least 100 samples to be collected. From these 100 samples, what would be the average household size or average household incomes? The same case of average vehicle ownership. That information can be comparable, or sometimes we can predict from the disaggregated models to the aggregated model. Again, you can go back, predict the aggregated case, then there is a kind of comparable thing sometimes. If it is okay, then you can use that. If it is not comparable, then you need to make some correction factors. So that's the way. So aggregated to the disaggregated cases, disaggregated to the aggregated models can be done. So the surveys are the traditional approach to obtain information on the demands for the public transport in general. So this is the general mobility indicators or what general data we generally focus mostly. So then the demographic and economy. So everybody knows that the demographic, social demographic variables are very, very relevant variables are important for the transportation models in general. So that may be like populations, area, population densities, like your population density, employment density of the particular selected areas, and the workforce, that is the average workman force of the particular zones. Even so, then the participation of workforce of the participations and the GDP of the particular area, and the slum population also important category. Like you need to know that actually what is the total unemployed of the particular categories of the zone. So that may give the idea, okay, what is average income level, how the average income levels might be changing, corresponding to the your different categories of the population. So then the separated, then we need to have the road and the passenger rail network. Suppose if you are focusing on the rail-based network system or rail-based the total passenger rail networks and the dedicated lanes for the transits, then the vehicle kilometer travel and the passenger kilometer travel for the public transit versus the private vehicles and the car, and the cost of the vehicle ownership and the cost for the public transit and the length of the cycle path. So suppose if you want to make a study relevant to the cycle, maybe like the bicycle lanes or the public bicycle lanes, then this kind of information will be required. And if you want to look at for the walkability index or the walking case, then the footpath availability, then the total length of the footpath, and what is the integration of the footpath with respect to the transit. So that kind of information to be collected. The travel speeds, so that may give the idea what is the change of the speeds at the different time periods of the day, probably. So then the number of registered passenger cars and the motorcycles. So this is also get the information directly from your secondary sources. Total number of registered cars and the number of registered vehicles as a motorcycle probably. And the vehicle ownership of the households and the model state system in the city or like the area. The average difference by most. It is very, very important information to be collected. The average difference by mode. It is not the average difference by entire city. we need to make the model based preference in general. So that way gives the better idea, like if you want to study relevant to the public transit, generally the preference are little higher than the preference corresponding to the maybe like two-wheeler or a car, which will be not that easy. The trips will be catered by two-wheelers at the longer distances than the public transit in general. So then the number of fatalities due to the road transport accidents. So this information will be important. Suppose if you are increasing a public transit network in the city, is there any chance to reducing of the number of accidents can be even correlated? So then the transport policy and regulations. So these are the data to be understood at the use level. Then if you make any kind of the regulation or policy making decisions, then this demands will be going to be shifted from the one to the other. Okay. Things are the parking. So we know that like make a kind of parking regulation charges increase in the particular city. What would be going to be happening in the car users versus the public transport? Identify. So then regulations are the entering cities, which means that entering of the cities. Okay, so I can make a policy to restrict the sum of the heavy vehicles, but instead of that, you can also keep on the entering of the some of the suburban vehicles to the urban area may be restricted as a congestion charge, so that we can cut off some of the vehicles by entering charges and the cost for the parkings. Of course, the regulations of the parking means removing of the parking locations. The cost means increase the parking cost. And other policies on the investment, so like maybe subsidies for the transit users, what is going to be happening, make the subsidies in the fuel consumption and the subsidies for the electrical vehicles users, then what is going to be happening. So these are the kind of policies can be taken into the account. Then we can change the travel patterns of the city and the travel behavior of the city. Any questions? So then if you had that kind of data with you, so then suppose if you want to understand that, so okay, this is my entire study area, within that area, then what are the kind of influence on the density, population density, are the other factors, density, total network densities of the transit versus the density of the private vehicles. Then for that, we need to collect the use relevant GS based data. So the data will be like I need to make that as Naveen sir to inform that actually like we need to make a buffer area, that is the influence area in the make a, suppose if you taking a kind of metro station, from the metro stations I can make the 500 meters as the buffer area. 500 meters, let us assume that your station point as the network of the like transit network of the metro. So then this is the station point. Then I can make a 500 meter radius from that. Then I will divide the area into the pockets. Then from the pockets, I can find out that what is the total land area, and from each pocket, what is the population. Then the denominator will be the total land area, then the numerator will be your population. Then I get my population. So in the total entire given area, so because sometimes you don't get the exact area divided with respect to the zone. Let us assume that, so you divided, this is the zone 1. So the zone 1 will be, the transit station will be subscribed like the including of the zone 1, zone 2, zone 3, maybe sometimes 5, 6 zones together. So you don't get the each station as a single zone. But if I am going into the disaggregated cases, then each zone have the different population. I'm going to select that because one station, if I am taking the 500 meter radius, then it might be including of different zones. There are 5, 6 zones together, I need to be considered. Then I need to select a population of each under the zone, and what is the area of each zone is coming under the within the 500 meter. Then that will be your average population value. Then the average area of the entire all the zones together, population density respect to that station. Yeah, you need to consider sometimes the people, because we don't have the very clear-cut information about the zones in the city like Hyderabad. So they divided the entire area into 4 major zones actually. So instead of that, what we done according to our studies, so we have taken the wards as the zones. Then let us assume that we have 64. We categorize as 64 zones. So then these 64 zones are like 64 wards need not to be the same category of the land use case. There are total, actually, according to the comprehensive mobility plan study by Hyderabad, they have divided into the 16 different land use cases. It is very difficult at the academic level to understand the 16 different land use. Then you need to consider the 16 into the majorly 5 categories or 6 categories. Then you need to make them, merge them, some of the land uses together. Then you need to find out, okay, according to this land use, then what is the total amount of the population density will be having, and what is the employment density, or is that what is the total amount of the commercial and land area you have, and corresponding to the designing of the commercial land area, what is the total number of bricks can be. That is up to you, your analysis. Each and every study have their own interesting of the elements or the points. According to that, we need to consider. Any questions? Anyone? Of course, we are going to look at that factors what we have taken. So this is the general kind of information to be extracted when you are dealing with respect to the transit means specifically. Okay. So let's see. So these are the characteristics what I am talking about. Land use like the probabilities in the residential area. So we can also extract that the residential density. What it means of the residential density? How can you extract the parameter as the residential density area? Is it the same like your residential area, total land use allocated for the residential area? That will be different again. Floor area, if you are considering, sometimes you have the high-rise building, sometimes you have the commercial high-rise building. So we need to segregate it. The residential area defined according to your total land use allocated as the 16 pockets or the 16 categories. Then sometimes we are merging together. Then I am going to consider, okay, this is the pocket of the land is specifically allocated for the residential area. Then how many number of buildings of the residential people are living in that particular area? So that divided by the total land area. So then you may get the residential density. So that sometimes there is a kind of small perception will be involved into that, because it is not that easy to get the information. So we need to identify every of the residential buildings, then that to be included as the area of the residential building. Like let us assume we have identified 10 buildings. That 10 buildings. So of course that if you are extracting that micro level information, then it is a tedious process in general. So we don't have the very freely available data in Indian case mostly. That's the reason we are struggling. So then the same way the commercial area, again it is very difficult actually. So suppose if you are taking entire city area is your study area, you need to understand that how much amount of the commercial area is there, what are the commercial according to the defined commercial category as the area of the commercial. The same way the recreational area and the development indicating that okay, this is the kind of area going to be developed in the next 5 to 10 years probably. Okay, so that may indicate that okay, this is the area emerging in the next 5 to 10 years. So then I can easily, or I need to understand it. What is the trip rate corresponding to this area in the next coming maybe 10 to 15 years? Sometimes the trip rates will be stabilized at some point of time, because if the densities are very higher and higher, so then there is no chances of the people are going to be occupied, the new people in the same area. The new people will be occupying in the vacant lands. Now the vacant land will be indicating the zero trips probably at present. There are no number of trips can be attracted to these areas. So then the other land use cases. The same way we need to understand that other land uses may be like the vertical land use cases and the mixed land use cases. So what is the total amount of the area you are going to allocate for the mixed cases? So that need to be estimated. Then if your land is serving for the mixed, mostly those lands can be minimized the total number of trips in them by specifically for the private vehicles. So then apart from that, we need to understand that like to be estimated as the network characteristics like the load side classifications. So everybody knows generally in the urban classification system we have the arterial, subarterial, electrical and all. So based on what is the total road density we have as the arterial subarterial and their properties, the number of lanes and the connectivities and the geometries. So what is the sometimes the geometry in terms of the intersection density are very important actually. Very basic question like more intersection density, what going to be happens or what expected to be happen? Maybe like the more kind of delay, more congestions can be expected. So then the travelers will be discouraged to travel using of that particular car or maybe that particular link. So that's the reason. So if you want to them discourage, so then generally provide more of intersection density, but it's not that easy to do that. So this road geometry will be also indicating that with respect to the number of intersections or like the road intersection densities and the railway system properties like the number of what is the density in terms of the stations area and what is the frequently or what is the distance between the two stations in general. So this kind of information to be extracted and the other network properties. Mostly the other network properties will be indicating where the kind of the links are attaching or maybe like other categories of the links are attaching to their arterial, subarterial categories. So mostly these other network properties are important when you are providing a new public transit network system in the city. Categories of the information which are important as the topographic features like the contours. So it is very important that actually the disruptions can be expected to happen if you have the heavy rains. So then we need to make sure that what is the gradients of the city levels, then corresponding to that where or how you are going to providing a drainage system to make sure the making the less disruption to the public transit network or like road network. Other information like the water bodies, drainage patterns, and the quarry identification, the forest cover. So these are some of the informations are also important. So mostly it might not be that important for the urban categories of the system, but still it is important when you are trying to understand a kind of the resilience of the transport network or the resilience of the transit system in general. So this is the general data what we are expected to collect from the surveys or like the. So now suppose it is very tedious process when you expect to collect the data or information from the OD surveys or like the home inventory surveys. So easily kind of method can be replaced this kind of the OD or maybe like the home inventory surveys to get the OD information. So the best way to collect the some of the recent techniques using of the. So there are many countries that having this smart card system. We just make the card. Even we also have the metro card. The same fashion it may work, but these card systems will have some information. But some of the advanced countries, like the very developed countries, they are also getting the information like the origin, destination point, everything. So then, if you have such, then I can make sure some kind of the data to be depends or rely on the smart card. So many large medium cities in the world, such as the London, so they have the Oyster cards, and the New York, Beijing, and the Hong Kong, all these countries they have their own smart card system. So this smart card system, sometimes we have the metro card, but it is not integrated with respect to the other categories of the mode. Like if you now the question has planning that actually they already have the smart card system as a kind of mobility as a service system. So now if you traveling in the multiple modes together, still the smart card can work or maybe like there are categories into the 4 categories of the more transit system and the public bus and even the yellow car, something like yellow bikes. There are 4 or 5 categories. So still some extent of the information we may get from that kind of smart card system. But it is only working for the specific to the some categories of the modes, then it is very difficult to extract the kind of body information in general. So these cards are based on the radio frequency identification. Basically, it is like RFID, like we all know the fast text how it generally works. The same is implemented here. So the passengers are required to tap the cards between the entry and the exit. So once they are tapping, then the entry point will be noted. So then the tapping at the exit or the destination twice. So again, it is exit point will be noted. So you know the entry, you know the exit. So what can I get? So if the spot is specifically for the transit, then I may get the transit entry point and transit exit point. But what is omitted here are like not collected. The first mile and the last mile information. If it is connected with respect to the other categories of the modes like auto rickshaw or like the maybe your ride service systems and all, so then I may expect that it is connected with respect to the first mile point as well as the last mile. So that means I may get the more reliable body information. So depending on the type of the smart card, it automatically and continuously collects the different bit records by using the public transit or like other categories of the modes. So some cards, that's the reason actually. For example, some cards will work only entry points, so they don't maybe not recording the exit points. Some cards will be having the both systems actually. So boarding time, the location of the stop and the transit mode, so the stop number, everything will be recording. So no information at the destination stop is recorded. So if it is such a way that, so then we are losing the destination choice or like the destination point, we don't get the OD, general OD of the system. So the information collected from the smart card can be used for the public transport planning other than the just kind of fare collection system. Like what sir has mentioned that earlier we have the fare collection system, ticketing punching system. So it may be noting, sometimes it might not be noting for each and every passenger. So generally earlier if you see the conductor will note down how many number of tickets are sold at that particular stop. Okay, so it is number of stop-based ticketing systems. It is very difficult. Again, okay, I need to subtract the total number of hours into each and every destination, how many number of tickets are sold. So based on that, I may get the some kind of the OD matrix. Might not be it is that not reliable actually. Because it is sometimes I might be noting, might not be noting, probably it might be omitted. It is very difficult to get the actual information. So there are different focused on the aspects to understand from the smart card system. So like these studies are focused on the passenger incident behavior. So then for that case, generally the methodology focused on the schedule-based assignment system. So then the potential is the estimate the cause of the incidents at risk. Like if anything happens, what is going to be happening, the frequency of your operational transit to the public transit users. So some of the studies are specifically for the OD matrix. Then the comparison with respect to the real-time data. Like they have the real-time data, then they have the smart card or like the mobile-based system data. Then they compared that what they have OD, they have estimated how actually it is reliable the information is getting from the your mobile or like the smart card data information. So there are some studies also focused on the examining the spatio-temporal behavioral travelers. Like sometimes it is very easy to get the information at the some point of non-congested hours, okay, or uncongested time. But it is very difficult to get the congested time because sometimes the information recording during the congestion is very tricky or like a complex job. So then the space, okay, the people how they are moving from the origin to the destinations, I may get it. But the temporal, in terms of each and every point of the time of the day, is very difficult. So that's what actually they visualize that the space or temporal cases. And some studies they specifically focusing on the reliability of the information by using of this kind of the big data sources. That is analyzing the travel time, reliability from the user's perspective. Even still we are doing some kind of the crowd-based source data. So based on that, we are trying to estimate the travel times for the. So we have not categorized it as of now as the more specific case. Like suppose if your bus is equipped with the GPS system, then I can know that what is the travel time at the different time periods of the city. In the same way, I can also know that how people are actually moving from the origin to the destination city. So that means if I have a crowdsourced based data, then I can easily estimate the travel times of the users of different categories of the modes, as well as I can also know that how these people are actually moving in a city at the different point of time. So what generally I can expect with that? Overall the mobility pattern, okay, good. trip patterns, okay. Trip pattern, mobility pattern, that is the same. Actually, I generally get that based on that information. So, what is the land use case of each case, and what is the time of the day the people are making the trip, and what mode actually they are using corresponding with the time of the day and corresponding to your land use case. That is the more reliable information I can expect to get based on this kind of the crowdsourced data. Let us assume that if I am asking the same person, so how much I can rely on the personal information as compared to the automatic information. I will also show one of the study according to one of our PG student what he has done. So then you will get to know that actually what they reported and what actually they are doing. So then the travel behavior, Gaussian's mixture of the models. This is generally this study they focused on the clustering of the passengers based on their temporal habits. So which means that actually they categorize it based on the passengers' informations. What is the kind of purpose of the trip they are making? So why is this purpose of the trip important? Like how many people actually travel during the weekdays for the work and the weekends for the maybe recreational purpose. Like there are some studies proven that actually during the COVID-19 there are more number of commuting-based trips are actually decreased, but whereas the recreational purpose trips are increased. Okay, even the people who are actually using the tele-networking system, doing work from home, they thought that so there is a decreasing of the total number of trips or the trips made by the person. But there are studies proven that actually the total number of trips made by this person of the recreational category has increased. Because at least everybody means it is not expected that every time I will be at home. I need to travel at least some point of time for my leisure purpose or some purpose. So there are these kind of the way to understand the passengers based on the temporal habits to be extracted even with respect to the if we have any kind of big data or maybe like the mobile based like the kind of smart card based system data. Of course, the route choice also can be expected to identify with that. And the travel behavior, that is the kind of measure of the consistency of the public transportation travel behavior. That is, what is the percentage of people they are using the public transit for the weekday commuting based purpose and the weekend for the recreational purpose. That can be expected to estimate with respect to this kind of sources of the smart card data. Then apart from that, we have also the mobile phone data, the smart mobile phone data. So everyone has carrying the individual mobiles. Everyone has one or two mobiles at least. So how we can extract the information from these mobile phones? Like everyone, if you open it the mobile, so then there is a Google location history. So that GLHS will give the idea how this person is making a different number of trips. So last 30 days data can be extracted. Like if you have the information of the city, at least 10% of the people data, then we can easily understand what is the choice of the trip and what is the choice of the mode, choice of the destination, and so on. So then, apart from that, so there are two types of the network-based data system we have. To contemporary of the public transport studies or like any other kind of survey-based data, that is call data records, and the global system for the mobile communication, the like GSM-based data, like we have mobile network-based data, or else the individual mobile Google location history data. Both can be used to estimate some maybe like the different types of the trips or like the different types of travel patterns. The CDR data compares the set of the phone activity, that is the phone call, text message. Like there are so many studies that are coming up that suppose if you are messaging in the Facebook or like the Instagram somewhere, so then okay, I enjoyed in the weekday, so and so. Then according to this data, then they're collecting pooling of the data, then they're categorizing the data, how people are moving at the weekends. Okay. So that's the way generally the text message data generally they're analyzing. And the internet accessing information even actually like of course some studies they have shown that actually how many people are interested to purchase online versus the offline system. So that may give the complete idea how people travel behavior changes when they have the online sources of the system of purchase. So then we have the travel behavior with respect to the estimating of the activities at the different locations and the combinations of the smartphone and the social media data even. So then we have the positions estimation. So that is how we can estimate a vehicle positions. Like suppose I want to know that actually the congestion levels of the city, then if I get the exact in my probe data, then I can easily make sure that actually how many number of stops the vehicle has made. The more number of stops, it may indicate the more delay that maybe leads to some kind of congestion levels at the city. Yes. So that can also has done by some of the people, some studies, and the accessibility. So even if you have a smart card based information particularly, so we can easily estimate that what is the accessibility of the spatial and the temporal cases at each case of the different modes even. So then there are some kind of the Wi-Fi and the Bluetooth based data also. Of course, we also have done some kind of the relevant to the Bluetooth based estimation data, Bluetooth based estimation data system. So then we have collected a Bluetooth predictors at the different 3-4 points. Then we have estimated like what is the travel speeds of the different people, because it is the catchy apps we have actually in Bluetooth. Then you just stand up at the one point, then it will be captured the coding of the what is the device it is using and what is the category of the mode, because the device corresponding to the mode is also designated too. So then based on that, so we have the timestamp 1 and the timestamp 2, 3, 4 like that. We have step up. Then we have chosen in such a way that one or two points without any kind of junction, and at least 1 or 2 points with the junction. Then we can estimating that actually the travel time when you are traveling in the particular specific car. So that's the way generally predicting of the some of the case of the Wi-Fi and the Bluetooth based data. So then, of course, this is very important actually. So what are the kind of issues with respect to privacy cases if you are using such kind of information of the data? So everybody is not ready to give the JLSS data to you. Right? Until unless if you know the person, if you request several times, then only the data will be supplied to you. Otherwise, you don't get the data, you can't analyze the data. Okay. It is very hurdle point with respect to the kind of privacy issues with respect to this kind of information. And apart from that, we have also the GPS. So that is the automatic vehicle location aerial information, that the GPS technology installed in the vehicle enables collecting of the time, location, service status of the transport modes. And this database is prepared by collecting of various geocoded information about the latitude, longitude, time, and the date of the specific GPS device what we generally installed in the system of the vehicle. So this AVL data is widely used in the conjunction with respect to the smart card data in the different outfits. Like mostly, like there is some studies going in the Hyderabad. Actually, they are almost equipped with respect to the 68 vehicles with the GPS, and they want to understand that how much amount of the stoppages of the bus system is there in the Hyderabad. So that may give the idea. Basically, they want to do this study with respect to the for the operational cost purposes. So based on the number of stops increases, then there is more amount of the operational cost that might be leading that the operator wants to minimize this particular cost. So for that actually your smart card data cannot be supplements that information actually. Like if you have the GPS based data, so that may give the complete more clarity about the number of stops and all. So then the GPS data has many other applications of respect to the car route mapping and the measuring of the taxi service, freight tracking system, commercial fleet management. There are so many kind of applications are there with respect to the GPS. So these are the different kind of studies that have focused on GPS based data systems. So I don't want to read too many here. So it is important to understand the model of how the individuals move in their time and the space. That is our interest. Like my interest is what is the time of the day the people are actually moving in the city and where they are actually moving. That is the time and the spatial, the temporal and the spatial cases of the movement of the people to understand the travel patterns of the particular city. In this context of the public transport, the travel pattern and the related statistical analysis are important, and adopting a plan to improve the current and the promote the new public transport system or the providing a seamless public transport system to the user in general. Of course, for that we need to have the data. So when you don't have the data, the supplementing of the public big data systems will be more reliable way of analyzing of the transit data information. So then it is also important that the performance assessment as part of or the integrated part of the system. So now if you want to analyze it, like okay, I am going to supplement the data to your big data. Then I'm asking to, can you able to evaluate the public transport system in infinity? Now, can you make some idea what you are going to do with that? Let us assume that I have supplied the data of the GPS based data. You have the lat, longitudinal, and time, and even the speed also to be given to you. Because I know the section length, then I know the time stamps, then I can get the speed. Then how you are going to start to analyze such kind of data? So the question is actually, I'm going to supplement a kind of GPS-based public transportation data to you. Then I'm asking that, can you able to evaluate the public transportation system in a given city? And the data is consisting of lat, long, the timestamps, and the speed. But because obviously you may get it. Because you know the timestamps, then you know the length, then you know the actual speed is designed, then you know the speed is running currently. Then based on that, you may get to know that what is the number of clocks of the delay schedule.
I would start with operational analysis of this. The route level stuff. Visualize the routes, look at intersection of routes, also look at stops which are highly serviced or under serviced. These kind of analysis can be able to do with these data and come up with policies related to route rationalization or which are the areas where I need more routes, which are the areas where I can cut short some of the routes. Or you can insert some truncated routes during some specific time schedules where the demand is high or the demand is low. So I guess these kind of studies can be done based on the particular purpose of
So is there any other point? So mostly we can analyze the stops, actually number of stops and the total amount of the delay is expected for the public transit system. So because I know the length and the timestamp, everything and the speed. So apart from that, if I am integrating, if you have some secondary source of the survey, or like maybe like the direct survey respondent data, then I can easily understand it actually actual demand, because you said that the demand can be cut off with respect to the demand, but for that I need to have the demand distribution process. Or else in the bigger picture, so you have the population data, then you know that whether this transit system according to the route network or like the transit network, whether it is serving for the actual populations of the residential and the commercial area as well as the employment zones, then you need to analyze in such a way, okay, this is the total amount of the trips can be generated, and this is the kind of serving to the public transit, and this is the kind of demand can be estimated as the actual macro level demand estimation model. So based on that, I can know that how many number of buses to be operated and how many currently I am operating, and what is the difference of the operation system. Okay. That's the generally, because no one will be ready to give that, okay, this is the information, this has to be set up, this is the kind of information to be lagged, or this to be collected, something like that. You need to understand according to your problem statement or corresponding to your objective what to be collected and what is the data you have in your hand. To be collected something else, then we need to look at that my secondary source. If you don't want to collect direct respondents information. Is it clear? Any point? Okay, let's start that. So this is one of the study what we have done here actually. So the case study is especially Hyderabad Metro. So basically this metro, like maybe you might be knowing that the transit oriented development TOD. So based on that, actually we are trying to evaluate the TOD system in Hyderabad Metro system for Hyderabad Metro. So for that we collected the different categories of the data. Let's start understand what we have collected the data first. So then first step, of course, there are the three types of the data has been collected corresponding to the understand the evaluations of the transit oriented development in Hyderabad city. That includes as the land use data and the transportation data and the orientation. There are three categories of the data. The same paper I have posted in the group. you can go through it actually, then you will get the more clarity what we have done there. So then the land use data, so data on the density, so then it is represented as the population density, residential density, employment, commercial. So these are the 4 or 5 categories we have collected. Of course, these categories are divided corresponding to the what we have done actually basically. First we have taken the current existing reports, and based on the existing reports, then we started understanding what is the land use condition of the Hyderabad. First, we derived it. We made that okay, these are the total number of land use cases of the city, and out of this, so what actually to be focused? How we have estimated that actually to be focused? That depends on that, okay, based on the total number of trips scattered corresponding to each type of the land use. So we have estimated that. From that, okay, we derived at least we need to capture a 60% of the trips corresponding to the different land uses. Because if you make all the land use cases, then it is very, very difficult to capturing of each case of the trip. So then based on that, we made, okay, at least this to be covered. Okay. Of course, it's not that easy to tell that, okay, you cover this 4 or 5 categories of the land uses. You need to have a lot of understanding of the travel patterns of the city and having the idea about the generally the secondary sources of the reports or the information, maybe like master plan of the city. Then you need to study first that. Then only you will get the basic idea of the city. The basic idea of the travel patterns of the city is very, very important to understand what data to be collected. So then the population density, so then for that actually we don't have any kind of the 2021 population data, but we have the 2011, then we forecasted. Simply we have started forecasting corresponding with the 2011 data to the 2021, then we again done the small scale of the 22 because this study has done at the 2020. So for that, we have taken the Hyderabad Metropolitan Development Authority HMDA data. So then the commercial density is determined to be a site surveys. That's the reason actually. We have done the different site surveys to understand the commercial densities, population densities, so many other parameters. Of course, the vertical land is mixes. So we taken each and every strip of the lands in the 500-meter radius. Then each and every building we have taken for the vertical land is mixes. So we have taken how many number of floors and what purpose each floor is serving. So then based on that we have come up with what is the vertical land mix of the particular zone. Then we average it, then you will get the average vertical land mix of the zone. Because we generally using that each and every corresponding to the station, the different zonal letters. So I need to know that for this station, how many number of zones it is serving, then corresponding to that average, what is the land, the population density, what is the average employment density, what is the average commercial density. I can't take that each and every zone employment like the commercial density to be included into the model. It is very difficult how to do that. So that's the way we have done it actually. So then the diversity represented as the horizontal landscape mix. There are 2 different types of mix in the diversity, that is horizontal and the vertical. Horizontal, which means that actually, okay, you have the different land use mixes. Then what is the average land use mix in the horizontal? Maybe like you have commercial, you have the residential, you have the vacant land use. So then what is the average land use mix of the particular zone? The same way the vertical land, so that is representing of the vacant. Of course, it is also apart from that, we have also taken the vacant land. So this vertical land is mix. Of course, there are some formulas we have to derive it to vertical land is mix, but for that still you need to understand what is the purpose of each floor of your vertically spaced buildings or space structure. Okay, so that is about the land use information. So as I said, it's not that easy to extract the information from the GS. It may take a lot of time to do that. So then the transportation data. So it is for the understanding of the transportation status of the city. So the desirability of the transit as one of the important parameters we have take home. So which is represented as the following indicator, that is the efficacy of the metro systems is represented by the travel time and the cost, and the transit supply adequacy and the passenger flows in the peak hours. So this is the information we have taken under the umbrella of the desirability of the transit. So then we have the comfort at the micro stations is represented with the basic amenities at the stations in the presence of the information display systems, ease of purchasing. Mostly this data we have collected on scale of 1 to 5. Of course, we have some kind of questions from the reviewers. So if we are collecting like the respondent data, what is the reliability of this information? So then we have checked that the reliability in terms of we have done in the very systematic way actually when we are collecting this kind of perception based data at the metro stations. So we categorize it, okay, what is the total number of travelers at each station? We collected as a gender wise, as the age wise, then the purpose wise. Then we disaggregated into okay, this much amount of the data to be collected from the survey at each case. So this is the percentage of the gender wise, percentage of the age wise, percentage of the purpose wise. We have taken majorly 3 categories. Then when we are doing this process, then it might be, so even some persons have not given much reliable information, but it will be aggregated. When you are aggregating, then it will be nullified some of the information. So that's the way we collected with respect to the respondents' information. But still, actually, it is very hard to get some of the information. The ease of purchasing the ticket, how to make this data as the quantity to it. It is very important. So ease of the purchasing of the ticket can be quantified. Very difficult. In my opinion, it is very difficult. So then we asked that whether this ease of ticketing at the particular station is compatible. Are you agree with that? Or ease of ticketing is there at the particular station? Are you agree, strongly agree, or disagree with that? So then the people are responded, maybe agree, disagree, according to the case of their purchasing capabilities.
Now they are using phone pay and other mediums to then regular card users. We are seeing how long we are standing. That would be some number. When you take it, this is the service mentioned, and when you are trying to do station wise analysis, because nature of the footprint at one station might differ to other station. So
Yeah, waiting time for the ticket, that can be even point. But actually, what happens? You have the letter in the according to our information. So there are passengers. When we are before collecting the data, we have collected the basic preliminary service. Then we have identified how many people are actually buying a ticket at the counter, buying a ticket at the directly Paytm, maybe phone pay something. So then it is we have to get the information the people who are buying at the counter. So when you are collecting the information at the counters and collecting the information who are buying at your phone pay something, so then there is a kind of difference of the opinions. Okay, when I'm purchasing a ticket by phone pay, I can say it is very easy. But who are purchasing at the counter, so I stand at least a 5 minutes time, it should be very less something. So this kind of, that's the reason actually. Instead of that, we made it as okay, whether it is comfort, easy of the ticketing purchasing at this station, are we agree with that?
In that case, you don't know. For example, if there are 5 people who are using PhonePe and 3 are using Phone, definitely we don't know. Their opinion will be.
That's the reason we made that one question before that, like the question is which method of phone pay or like the ticketing. So we aggregated the information. So then there is no issue actually if I get the 30% as the phone pay and the 50% as the counter ticketing persons. Yeah. So because that makes that actually the reliability of collecting of the information. Even when you are collecting this information actually, like let us assume that, so when you have the 5 different zones, then I am assuming that actually I am extracting the information very accurately of each and every zone of the population, and I am making that the particular area of the zone. But when I am going to the next station, so I have the 2 stations or maybe like 2 zones. One zone having the 95% is occupied and the other zone is the 5% is occupied. Can I omit this 5%? Because 95 is contributed in the zone 1 and the 5% is coming in the zone 2, because digitizing of this 5% of area may take at least 2-3 days. Can I omit it? If you are omitting, so then the consistency of the data is not there. So that's the way the consistency problem, the reliability of the information problem will come. So if you want to collect more accurately, first you need to have the base information of the system. That makes you understand that, okay, what to be collected, how to be collected. So then the orientation data, so that might be like the design represented by the motorized and non-motorized transport system of the network densities. So we have collected the what is the total amount of the motorized network density and non-motorized network densities. So in terms of the public network density and the percentage of the public spaces and the frequency of the shuttle operator at the bus services from the transit stations and energy safety at the intersections. So these are all comes under the categories we have taken into the design case. And the distance to transit, so represented by the nearest transit stop from the different land use types, and the destination accessibility represented by the frequency of the transit service, and access to the various destinations by the transit stations by walk and cycle is collected, and the demand management represented by the parking supply and the parking demand is collected, and the dissonance represented by the percentage of the stations are the residents who desire to live but they are not living. So that means we have asked in such a way that are you desire to live within the permissible area of the station? If they making that, okay, I agree with that actually. But they want to travel by your transit system, but the question is actually the reverse that. Okay, if you want to desire to stay very close to the station, but that you're not making the using of the transit system, what makes you difficult to use that or not using of transit system? So that information we also taken as a dissonance case actually. So then the difference to the environment represents the prevention of the air pollution, vehicle emissions, and the e-bike public bicycle sharing system. These are some of the information we collected. So then if you count all together, so these are like the 9 different Ds. So from the density to the up to the difference to the environment. So these 9 Ds we have used to evaluate the TOD system. Of course.
Non-reference network that based on presence of sidewalks, footpaths, or elevated structure considering the non-motorized. Because if you consider sidewalks,
Yeah, I understood. Based on the bicycle system, you're asking probably.
if you consider sidewalks as a facility for non-motorized transport, so you can say that suppose road network has a sidewalk and in that way it caters to the non-motorized transport. So did you consider that segment, or it is just based on sidewalks which are exclusively there for pedestrians?
Actually, some 1 or 2 stations, what we observed actually, we have the bicycle system also. So that we taken what is the total length of the bicycle network at the particular station particularly. So then apart from that, few stations do not have any kind of like the walkway or like the footpath system which are connecting to the stations specifically. So there might be like let us assume that we have taken the 500-meter radius. When we have considered the 500-meter radius, the other station also 500-meter radius. The 2 station distance is the 1 kilometer. So when we are taking into the account, so then the footpath is available up to a distance of the 200 meter, 300 meter, very nice footpath. Then afterwards it is completely disappearing, which means that within my 500-meter radius of the buffer area, so I have the some length of the footpath as the density design of the non-motorized transport, but remaining is not there actually. So then I can take that to total length and available.
You mentioned 500 meters. Is this sort of evaluated based on Indian condition or we follow the standard literature? Because if you go into the literature, the standard practices here in US or it is half a mile is considered as a buffer for any driver. So is that based on that, or you try to come up with Indian scenario based on which you come up with that?
Okay, so for that actually we started exploring of the information from the users. They hard to walk with 500 meters. Initial, whatever the preliminary setups are there, what we have done. So hardly they mentioned 250 meters, 300 meters, not more than that. But still, what we have done is actually, so the way which we have selected, so we collected the literature as you said. So there are studies have done for the 800 meters, 600 meters, 500 meters, even some studies very few at the 200, 300 meters. So we have selected in such a way, even if I go with the 800 meters, the other station will be including the buffer area of this study area. So it should not be active. So then when we are taking the radius of the 500 meters, it is exactly meeting of the other station area. So then we have chosen, okay, 500 meters is a more appropriate than the users what actually they are pursuing to walk. Maybe like that is the 200 or 300 meters. So in such a way, we have chosen the 500 meters. Yes, overlap. It makes sense?
Yes, so we did some hey, I'm not a what I would call, I don't know if I should call him a transit person if you will. So I think it's arbitrary to say it should be some distance. So the scale of impact of each variable could be different. So for example, there could be variables that have impact at 500 meters. There could be other variables which could be having an impact at a 800 meter level. So in one of our works, we got a lot of comments criticizing, discussing about it. What is the theoretical support for it? But what is the theoretical support for using only 5 or half a mile? It's a applied thought process. So I would suggest, again, if data processing is not too burdensome, so some of the techniques, if you're using JS, you have good databases, layers of data is available, you can draw buffers at 400 meters, 800 meters, easy. If again, depending on what you're trying to do. If it is available, test more, test multiple. I mean, why should bus stop density only be significant at 400 meters or 800 meters? So my approach would be, let the data tell you what is significant. So we run a model where tomorrow's class I'll show you where we check 200, 400, 600, 800 for all variables, and we selected one that offered the best fit. So for some variables we got significance at the 200 level, some variables we got at the 800. Again, practitioners find that a little hard to understand. That's what my personal experience has been. Because again, you need to look at data difference. But what I'm thinking is the idea that people's perception, or nobody's drawing these buffers, right? And if I'm a bullet translator, I'm not really drawing, oh, I am living 450 meters from the stop, this stop, so I will behave this. No, it's a way for us to capture what is around the station. So I think we are limiting to our own understanding and saying everything has to be around 500 meters. So if data permits, I will suggest looking at multiple buffers for different variables, and then let data tell you. So whatever gives you the best fit, you choose that. So that way, people are, you can think of this as, if you want to give data support, it's like for different variables, people are using different layers of perception. Right? So when they're looking for a grocery shop, they don't want to go more than 300 meters. But if they're going for a hardware shop, then they don't expect it to be there right next to the house. So people are following different distance metrics for different things. So why should we impose one for every? Right? So we can explain that in that fashion. And again, I think if you're doing a data-driven model, at the end of the day, most of the things that we do are data supported. So let data let you guide you to what is the model. That would be my take on this.
Yeah, for that actually, what we need to have the complete setup of the GS data source or information. So then, we need to have the identify the database of the requirements and the requirements in the sense. Okay, if you want to make the layers of the data, what kind of the JS secondary source information will be required, like the network layer, the zonal layers, and the multiple different types of the JS layers. Then you overlap it and understand the different types of the your zonal information and the network density information. So huge amount of the secondary source information and like the maps will be required to get the JS source data. So identify the appropriate data sources and develop the conceptual database designs and develop the physical database designs. The physical database design sometimes you can't display each and every information 100% accurately until unless if you have the understanding of the physical information at the source at the ground level. So then that is easy to do kind of digitization in the GS in general. And the procure the conversation services, the GS available information, then the develop the data conversion plans, and the comments of the source of the preparations of the maybe like your journal based information in terms of the population. So because you need to overlap the population information on your the journal based data, then to understand what is the total amount of the population with the selected or identified areas. Then the different activities information corresponding to the land uses and the finalizations of the acceptance of the criteria. Because what would be the criteria to choose? This is the kind of the total population density when it is having the subdivision with respect to the different zones. Then I need to have the criteria. Okay, at least I need to take the maybe some amount of the area even if it is coming. So when we are doing this process, actually, what we have difficulty faced actually when we are taking the station. Like let us take the buffer area of the 500 meter radius. Then I have the some of the zones having the 80% occupied, 20% occupied, but some zone having the 1% occupied. For that, sometimes whether because 1% occupied on the digitized information of the GS maps is very difficult to extract the areas and the population is the 1%. Because we have the population of the zones if I'm taking, so that is the ward population we have taken generally. Let us assume that we have the 1 lakh population of the ward. For the 1% of the area, so how can you choose the population? Then how we are going to aggregate with respect to the remaining zones? Then this is a very tedious task what we have faced. Of course, what one of my students has faced at the time. So then the comments of the database maintenance, of course, this is very important. Each and every time we need to update some of the information, particularly with respect to the network information. So then finally we need to have the final database system to understand your corresponding what is the source of the GS information will be required for your analysis purpose. So then this is the kind of identifications of the data, that is internal and external sources, and the checking for the completeness of the data and the quality of the data. The new data via field or the aerial surveys to be identified. Of course, that is not our job. If you have the directly available sources of the information, then you extract from that. If it is not there, then you have to purchase it sometime. So recently we have done some study relevant to the extracting of the air pollution information from the this remote sensing based data. So whenever we are facing some information, loss of information, then we procure the information from the other sources. Like so, we have the different levels of the scale of the information, specifically for the remote sensing or the GS based information system. For that, we need to go either we need to procure the data, or if you want to get your own data, you need to go for the aerial surveys. And the fixing of the problems in the data sources, that is the map scrubbing. So that is very important. The cleaning of the information of the source from the corresponding raw information of the data source. The coding and like if you have at least a kind of some idea about your JS coding system, then you will understand the labeling, so network labeling system. Then you need to code for each case. Then you need to make the big picture of the entire road network data, like your transit network data. So the unique IDs very important pieces. If you are not giving the unique IDs, then when you are overlapping of the one map to the other lab, then you will get to you may get more number of problems. So can you give some idea on that how it can be possible if you are not preparing a unique ID systems in the database? Like you coded a arterial network as the 1 code sometimes, then you misplace the arterial codes instead of 1 as the 2, then you may be losing of the entire section or district. Yes, sir. So that is the way the consistency problems also will be encountered in general. And the converting into the digital forms, that is the scanning and the digitizing of the data, so the raster to the vector conversion strategies, entry of the attribute information. So the linking of the attribute data in the GS code or the GS information is one of the important tedious process. So your most of the time will be consumed here. Of course, until unless if you don't have any base data information. If you have the base data, then it is very easy because I'm extracting from the base information. If you don't have base information, then I need to do everything. So I'm preparing my own database system. For that, I need to code it. I need to make the unit coding system. Then I need to make the attributes information of each and every case. In the data conversion specification, there is the horizontal vertical controls, then the projections of the coordinate system, and the accuracy requirements. So mostly when you are dealing with respect to the okay, suppose in the system of the contour you have, then based on that I have a gradient system. Then based on that I can get to know that what is my fuel consumption of the city in the entire transit network. Suppose if you want to do that, I need to have the what is the level at the one point and what is the level difference at the other point. Then I am making that at each and every section the gradients. Then I know the total gradients of the city. Then I can get to know that what is the total amount of the fuel consumption because of the increasing of the gradients of the city. Of course, that is not in controlling our hand, but still we can understand it. Of course, the accuracy requirement is very important. Then the documents flow control. So these are like the information generally expected to make in the GS data system. So like the monitor flow maps and the digital files and the change of the control of the changes of the data, the controlling of the time period, different time periods, and the quality control procedures and the potential highly complex systems. So then the generally a combo of the automated and the manual processes. Mostly we need to make generally what we have done as the manual digitizing, manual activity, manual coding system we have done it. But there are some ways we need to automatic coding of the some of the information. At the time, still we need to make the internal checking consistency. Internal consistency is very, very important process when you are doing this kind of coding systems. And the problem resolution process and the correction responsibilities need to be defined. So then what are the kind of the corrections to be applied? Suppose when you are collecting the survey data, we know that what is the way to be correct the data. It is very simple. So the simplest way is the, okay, you collected the information. First of all, I need to screen the data. The screening of the data can be done. Okay, I have my employment status of the particular survey data. Then I select the employment status. Then I will collect that what is the category of the person responding. The employmentability is there. Then the category is the kind of the average income levels of the people. Then I can cross check that income levels with respect to the category of the person, the employmentability of the person. So if he is given as the respondent as a student, but he is responded as the average income level of the income of the person as the like more than 1 lakh. So there is a kind of discrepancy in your data collection process. The same way we can make some kind of the correction responsibility in your coding also, where I need to check the cross checking my data. So that has to be defined first. So then once we have done that, then it is the final acceptance of your GS data for the your next process, for the analysis process. So okay, we'll stop here actually. We'll continue maybe in the afternoon. So do you have any points to be discussed or like any questions?
In the slide number 7, you mentioned about land use characteristics, classification, the classification for the Indian state. What is the source of code?
Generally, we identified the 16 different land use characteristics or land use cases according to the master plans of the HMDA. So if you collect the master plan details of your city, suppose if you have, then the master plan, they might have defined actually what are the different types of the land use cases they are considering to the account when they are doing a service. They are doing the different categories of the surveys like the OD survey pattern, travel letter surveys, or like the streamline surveys. There are different surveys they may generally do it. So based on the land use cases, they will define it. In the report, you can easily upload. It's very, very difficult. We have some digitalized information of the Hyderabad, but still we have to do more than 50% of the digitalized information. Actually, it is the partial level, sir, because we have the incomplete the zonal information. So what we have done actually, we have collected the ward specific information. Then we have digitized in respect to the wards. Then we have the transit network data. Then we overlapped on that. Then we collected the densities. because what level population we have, and we have the even the what are the major locations of the land use, what they have provided on the base information. Then from that again we collected the ground based data to some extent.
Use it's a little easier because you get part level data for entire state of Florida subject. So not just one city, we just did the project where we modeled parcel evolution, how each parcel is changing over time. We had 10 years of data. We used that to look at each. So each parcel is each site, each plot, like it's a house. We have that. So there we had 100 land use classifications. So we had to reorganize the classification. We can't model 100 dimensions. So we made it into 14, something like similar to what program so. But yeah, I think data is the challenge. I think if data is good, digital data is available, you can do a lot with it. But that, yeah,
So we wait for lunch. Lunch is arranged and see this data. We need to understand where generally this GL-based data will be getting collected. So the sources are very important. Sometimes we need to make the resolution. If you want to make more resolution data, then the cost might increases. Then we need to look at that the applicability of such cases of the resolution. So when we are going for the very recent experience of the emissions based data, when we are collecting from the emissions based information, so then when you are collecting a 1.5 meter by 1.5 meter grid size data, then it is much costlier than if you want to collect the maybe like 5 kilometer radius, 5 by 5 kilometers grid data. So in such a way, like sometimes if you are going with the 5 kilometer by 5 kilometer, then the applicability in terms of extracting the information of the relevant to the pollution, so it is very difficult. So we need to have the 1.5 by 1.5 grid size data generally. So that's the reason the applicability, suitability, and the increasing of the amount of the data corresponding to that. These are some of the important information we need to look at when you are going for the this particular GS-based data. So the sources might be like the map and the drawings are like the aerial photography system and the satellite imagery and the CAD database when you're specifically looking for the network-based data system. And of course, the government commercial spatial, like everybody knows that actually the Survey of India will have a huge amount of information relevant to this GS-based data system. So then the commercial activity database system respectively even some like if you want to collect the relevant to the land use information of the Hyderabad, specifically we need to either request from the GHMC, they will provide some extent of the data. So if you don't have that system, then we need to go with the like specifically one category of the data. We requested the electrical bills. Of course, they have not given for all the watts information, but they have provided some kind of the watts. So this electrical bill data we have collected for the reason is here. So to understand that the way like we started with understanding of the relevance, the relation between the TOD versus the gentrification. So when you are trying to look at the gentrification point, so then is there any way the gentrified is happen of the particular study area locations? So that we are trying to understand with respect to the current bill, like the electrical bill, corresponding to the house rental system and the land values and all. So based on that information, so we are trying to extracting or understanding the information when it can be happens the gentrification for the system of for the selected TOD areas. Of course, this is the way still the remaining information like the maps and drawings, the digitizing and the scanning the available raster to the vector information. If it is aerial photography, the photogrammetry and the photography implementations of the system, the digitizing and the scanning of the conversions in the digital systems. Of course, these are the kind of the micro level information we may get from this. What are the sources of the data we have? So, like, let us see the one case of this respect to Bangalore, what they have done to understand the kind of the BMTAC, like what the have the bus system. So, the public perception about the BMTC, they have evaluated actually. So they have collected almost like 196 samples by a total of 50 questions they have used it. So I told already, so most of the time, so when we are collecting the this survey data actually, it is all about the respondents information. But still actually, like if the respondents information you don't want to relate too much, then I need to make all this kind of information, then I need to make the quantifications of the information. So the questionnaire which was developed consisting of the two sets of the items. So then each one is consisting of the 25 questions. So then the demographic profiles of the respondents they have collected and the types of the buses used from by the respondents have collected and the frequency of the bus travel also collected. So this is the kind of the information they have collected. So that is the bus information scheduling and the route maps are available, and so like the reliability of the dimension they have collected. So corresponding to the scheduling system and the route maps are available from the bus system. And the time during of the peak hours, they also collected that what is the time scheduling during the peak hour systems, and the availability of the buses, maybe like in terms of the network coverage systems, they are collected. So then this is the kind of the average perception and the average expectation scores. So what they have done actually, what the public is averagely perceiving the system. Okay, so is it maybe according to you, are you satisfying the coverage of the bus network system in the city? Okay, then 1 to 5 scale, okay, which is okay for me, like maybe 3 or something like that. The expectations maybe scores, you see actually the scores are very, very high. So then the scores, the expectations minus your average perception score, then the differences of the opinions can be expected. So generally the expectation scores they have given actually, okay, what actually you are assuming and what actually you are expecting. You are using the system as the coverage is the satisfying, maybe like the 1 to 5 scale if I ask, okay, you might have given the 3, but according to you, is it sufficient or you need to have a more number of bus coverage system, like the more number of operation in terms of the frequency or the more number of buses to be operated in each corner of the city is something. So this expectations is not corresponding to the operator point of view. It is again public's point of view. So we need to derive the expectations of the each question. Yeah, that is the your scale is different. But the problem is actually sometimes this is the kind of another issue we can expect in like the this scale should be according to generally the scale should be in the equal case. Otherwise, again, there is a lot of difference in the opinions made. Of course, it again depends on the how and what basis you are designing the system. Like if you want to evaluate that the expectations of the public perception are meeting the demands at the corresponding to the operator perception. So generally, of course, it is not 1 to 5 scale. They have calculated a 1 to 7 scale. So that's the reason the 1 to 7 scale. So basically, people they have the once the collecting of the survey system, they have the mostly 1 to 5 scale data, 7 or even 9 data also. So 9 generally we don't go beyond the 7 scale system. Of course, it is everybody they have their own perception.
Nearest value to rate actually. And the means average means mean value of the entire rating.
The mean
We need to take weighted mode or weighted average.
generally the weighted average is the more reliable compared to the direct averages. Because if you take the direct averages, obviously it is combining up together. But it is, I'm not talking about it is just weighted average or mean. So it is a total value corresponding to your expected value to the difference of your perception. The perception, what actually you are on the system on the ground level. So like they have collected huge information actually. Like the majorly they collected in terms of the reliability point of view and the tangible dimensions and the responsiveness of the dimensions and the endurance and the qualitative point of it. So this is the kind of information they have collected from the public's opinion. So this is the one of the case study I have taken from the one of the paper relevant which they have done from the Bangalore point. Bangalore. The primary investigation. So this is another work what we have done in our own student actually. The GLHS data can supplement the travel surveys. So what we have done is actually the preliminary investigations we have taken out first. The accuracy of the GLHS data is assessed with respect to the GPS based survey. So basically there are three different categories of the information we have collected. The first setup we have done in the GPS based survey we have done. The same persons, then we have floated a questionnaire in Google form. Then we have asked for the last 1 week what are the kind of the activities he or she has done. That information we requested. Then the same person we also requested their GLHS information. There are three categories of the information. One is the GPS based information, and another one is the Google form based information like the questionnaire survey. Then the third one is the GLHS, that is the Google location history information from their mobiles. So then this GPS loggers is used for the survey. So at least this GPS we supplied to them, then they carried out at least a week. So like 15, total 15 members we have supplied the GPS. Like we circulated for the different time periods. See, if I know person, if I requesting you, we can't deny it. So like we catch up the persons, like those who are not, like it is kind of a snowball method. So based on the snowball techniques, we identify the people who are ready to give the information. If they are denying, that's fine. We can't force them anymore. So that's the way we collected very few samples of the GLHS. So it's very hard to get the GLHS information of the people. Then the 25 days travel behavior data is gathered. So we collected a few people 25 days, and few people very less number of people they have given for the 25 days, but we also collected the 7 days more reliable information. And the raw GPS that is processed using the rule-based algorithms, and the process for the trip information validated using the prompt recall survey systems, and the GLHS data in the KML format is collected. So the trip details from GLHS are extracted. Let's see what we have done for this. And from the raw GPS data, so that is the coordinates, elevation, and the leg distance, that is the section distance value or the section length, and the leg time, leg speeds, and the leg course times are extracted. So this is the kind of sample course of the data we have extracted from the GPS. So then once we collected the GPS information, then we have processed for that. So then we are trying to understand their origin and destination, because we know the coordinates of the each and every person. So like to whom we have supplied the GPS, and the start time and of the trip and end time of the trip also we have extracted, and the trip length. So that is correspondingly each person who carried out the GPS. From that, then we have extracted the trip length and the trip time and the average speeds and the mode also. So we have used a kind of rule-based algorithm. If the speed of the travel, speed of the person is respective to the different categories, we categorize the modes actually. Of course, it is not 100% true, but we extracted it as much as closer, because the same person data we have from the Google form. So then this is the kind of the rule-based algorithm has applied. So then the raw data we process. So then once it is processed, then we have taken the trip length. So the trip length we taken with respect to the speed is less than 2 kilometers per hour. So then we have taken, if it is fast, okay, if it is less than 2 kilometers per hour, which means that we categorize it that might not be taking a complete trip. It is stagnated trip. So that's the way we started. We made the algorithm. So then if you see here, actually the travel times and the travel distance are increasing with respect to the increasing of the distance. Then the time might increases. Then we categorize it as the trip actually. Like at least let us assume that the person is traveled at a 2 kilometer distance, then he stagnated there. which means that it might have walked at the 2 kilometer distance. So that's the way we categorize the total length of the trip as well as the mode that might have used for the trip like that. So then once that is the one side of the data we have extracted or collected from the GPS based information. So then we have also collected the same persons of the GLHS information as the KML format. So this is the kind of the information may generally look like when you are trying to processing of the your KML files. So then the 82 trips were recorded based on the like the preliminary survey or maybe like the pre-resume survey. So sorry, like the pre-selected people surveys. The GLHS data showed the higher accuracy in detecting the trips compared to the GPS logger. So if you see that actually that is the parameters at the trips. The GPS logger is shown the 70.70%, but the GLHS data is the 90.24. And the mode used prediction is the 72 by the GPS loggers and the GLHS 1068. So there is some issue at the GLHS information. Mostly the people will walk. Again, they will catch up some kind of modes, maybe like kind of probably the auto rickshaw probably. So every time it will be stagnated. Means so mostly if you see in the auto rickshaw in cities like Warangal, after a small distance traveled, then it will be stopped sometime. Again, it will be traveled. So categorizing that as the vehicle and the traveling the sections is much complex process when we have started using of the GLHS. So that's the reason the prediction capability by GLHS to understand the mode is very difficult. Means what are the studies we have done from our side. So mode detection accuracy was highest in the case of the walking, cycling, and the public transit. So that's what we estimated here. So the mode detection accuracy was very poor in the case of the motorized two-wheelers in the past because it is very difficult to identify the average speeds of both the modes are very closer. So we are unable to predict that whether it is two-wheeler or like whether it is car. So this is the kind of code we have made. So then to convert the formatting of the collected data. So then the processing of the raw GLHS data. So formatting time and the coordinates and the extractions of the relevant raw data and establishing additional parameters, the parameters in terms of the travel time specifically, and obtaining the raw data for the concerned speed. So that means mostly the GLHS data once they supplied is 30 days data in general. So then we are trying to understand where we have the GPS data plus where we have the same duration of the Google form data. So these three has to be checked parallelly. So that's the way. So we are trying to understand from the obtaining raw data the concerned weeks because only we assessed the 1 week data because the only 1 week data of the Google form data is available, that is the response data. Then the check for the trip ends and the check for the mode use and the extractions of the trip information. That is what we have done at the end. So then this is the kind of the results we got. So Monday, so that is the number of trips made by cycling is 2, and the Tuesday, so then this is the kind of the number of trips made by cycling, then the vehicle, like vehicle and the motorcycling and the walking like that. So these are the trips we predicted as mode wise. So this is the total number of trips predicted. So that is the Monday, 3 trips, Tuesday. Just for example, I am showing the 1% data actually, but we have multiple number of it is used information. So we have collected very few members of the 1 week. Still, it has the huge number of data. So the Tuesday 6 and the Wednesday 6, like this is the total number of trips made by person. Like if you see that the number of trips made by this person is higher than other. So we need to, of course, it's very difficult to assess in such a way that whether this person is category comes under the student or like working employee, something like that. But generally, if you analyze, like the Monday, he made 3 trips, Tuesday 6, Wednesday 6, Thursday 6, probably Friday 6, which means that it is the kind of commuter workplace trip. This person comes under the category as the commuter work. So we can also categorize in such a way actually. So if you also, if I'm making this data on the projecting, and we have also done the overlapping on the Google map, or maybe like your total Warangal city, then we also estimated that their original destinations are. So where their people are coming, where their people are going, like. Of course, this is the part of one of our MTech student work. So then this is the okay. That is the one part. So like what I have shown in the morning session, like the big data collection system. Like if you are interested into collect such kind of the mobile based information system, then we can also make the understanding of the number of trips and what is the trip length and what is the body matrix of the people of the city, particular city, also can be extracted. And this is the other kind of the work with one of the PG students. So we have also done like the mass, how people are interested to use the adopting of the mass system in the city like the Hyderabad. So first of all, we need to have the kind of understanding of the mass. So that is the understanding of the mass. So it can be integrated, what kind of the categories of the modes can be integrated and how it generally works. It is simply as the journey planning system actually, mass. If you have the mass, we have the more reliable information of the transit system along with the paratransit can be available. So then the ticketing system more reliable way of the like the paying for the ticketing and the kind of information about the time scheduling and everything can be available. And it is also very important that the connectivity as the first mile and the last mile and the transfers of these any specific stops. And also we will get the more information about the transit availability of the city. So generally it may be like the challenges can be, we can see like with respect to the urbanization. So mostly the increasing of the population, the increasing of the urban sprawl can be expected, then it may lead to the congestion. So then it may interesting that the people to move towards the or to work out to minimize the congestion or like minimization of the adverse effects by addressing of the electrical vehicle system or like automated vehicle system or like shared mobility. It is simply considering as the technological transformation. So once we have such kind of the technological transformation, so something kind of app or maybe like the technological system should be having the connecting of all together. Like I need to have the kind of system of the automated vehicles to be operated as the maybe like your shared mobility system or maybe like the other category of the vehicles with respect to the electrical vehicles. And if you combine together as the probably as the mass, then it is more advantages we may generally get in terms of minimizing the congestion or adverse effect. So generally it is the traditional way of commuting of for an average Indian involves in the combination of the different transport modes. Like how many people are involving in terms of the different categories of the modes from home to the your actual transit stop, again transit stop to the office. Like it is the connecting of your first mile and connecting of your last mile. So if you want to increase the demand to the transit, so then I need to make the more connectivity and integrating of all these categories of the modes together. So then the demand for the specific transit modes will be increases in general. So it can be happens or like it can be expected to happen with respect to the kind of this kind of apps like the mobility as service. So then these are the modes for convergence and the trial to your needs of the mobility packages. So then convergence in the sense again it is the connecting together seamless operation system in terms of the reliable time scheduling and the ticketing prices and everything. And this mobility service gives you access to all modes and the real-time information for the journey as well as providing the instant journey plans and the booking systems at one place or at one hand in this at a time. So it is the evolving of the concept in the transport sector, which basically provides the different travel options. So generally, when you are choosing a single individual modes, then you have the very limited options. Like if I want to travel by transit, so I want to look at only the scheduling of the transit system. I don't have any idea, or I don't have any information about the other categories of the modes or like the paratransit, probably, which are not connected to the transit system. So MAS is an integrated transport solution that combines the different transport modes in a single mobility package. So mostly in terms of the scheduling and the ticketing point of view. So with the MAS, we can easily plan the trip. So then we can easily book the ticketing for the trip. Then we can easily also pay. So then generally this is the kind of the situation with respect to the MAS, which will be connecting of the higher category of the rapid transit to the bus transit system, then the the shared mobility system, then even the public bicycle sharing system probably. So then the situations with respect to the mass will be connected. So then we can choose the different plans. So I may go, suppose if I am planning with respect to the traveling by metro, then I can easily understand which are the connected modes, or maybe to travel or towards the metro station, then these are the available modes may show. So if you are traveling by bus, so this is the time it may take. Then if you are traveling by shared mobility like Ola Uber, so this is the travel time it may take. And if you are traveling by using of the bicycle sharing system, so this is the travel time. And respect to that, you will also get the what is the package in terms of the cost. So like if you're traveling in the Netherlands, particularly like Amsterdam, so then there is a one app actually. So you just need to install that. So then it may connecting with the like the sprint, the sprint, and there are different options actually. So then you will have the options of the bus and the options of the bicycle, options of the even shared mobility system, everything you will get in one hand. So then you can easily plan it. If you want to travel by sprint, by from your given origin to the destination, then you will get to know what is the price of your trip. Then even if you change the option instead of the bus, then you will travel at least some extent of the maybe other category of the mode. Then you will get the total your price or like the cost of the trip. So it is a different, of course, the mass what we have or what we are trying to implement in some of the cities like Kochi. So we are at the very basic level. It is not like very high level of the mass system. So there are different like the levels of the mass. Like the first of all, there is no integration. There is a zero level. Then we have the integration with respect to the information, not the modes directly. So like integration of the information means you generally get the plan, or you can make a plan in such a way. The scheduling system. Okay, at the time of the 9 o'clock, you have the or maybe like metro. So then, if you want to catch up that 9 o'clock metro, then this is the kind of options of the other modes you might be having, and this is the travel time, expected travel. So, like that kind of integration information can be given. So then the next level is the integration in the booking and the payment. So the third level category will be you can also make the booking of your trip with respect to the available modes. Then the fourth category, you will have the passes bundling system. Like I can make the pass for the next 1 month, or I can make the pass for the week, something like that. So you have bundles of the options to choose respect to the plan for the payment systems. So then the other category, that is the highest level integration with respect to the societal goals, like suppose the same app can be used to book for the cylinder, or like the paying for your maybe any kind of OTT channel payment, everything at one platform. Like nowadays, even if you open a phone pay, everything is available at phone pay. Like you can pay for the booking, you can book for the movie ticket, you can book for the trip tickets like metro probably. So even you can make your FASTag payment like that kind of the app. But these apps are completely different. How it is different? So even if you open your phone pay, everything is there. But this mass will be different than the phone pays app. How? It is not integrated with any modes. It is not giving any scheduling of your trips. But that is very important as a plan, like the transportation planner. So how to integrate them and how to make the scheduling them. The best way of the scheduling or integration of the information scheduling. So then it makes that the journey planning, that is the real-time journey planning, allows the user to plan their journey and the ease of transactions and the flexible payment terms, the user experiences, and the personalized services. So these are the different types of the services can be expected by mass. So this is the way generally the mass apps may look like. So this is the upcoming journey. So this is the like the home from your place. Then the journey will be started at this time, and the total amount of time it takes. And the ticket is booking. So then it is also showing that what is the pickup time if you are booking as the radical service at the beginning or the first mail service case. So then you can also discover that what are the nearby kind of interesting places for you. Then corresponding to the nearby places, then what is the best option for to book your journey category. So then we have the different types of the subscription options, like 7 days, 20 days, something like. So then finally you can make monthly plans and then pay for the rights. So generally, how it works, the main complexity, anybody can point out that, like, what is the main complex point of this? Which level is the more complex? We have the main levels. Simple integrating of the information is very easy. Infrastructure. Okay. Okay. Integration of booking of multiple modes. Okay. Booking according to the demand. Booking according to the demand. Okay. Even I can book that ticket. That's not a problem. Because if you are integrating the information, then corresponding to the information, you make the okay. This is the total payment to be made. But you try to understand that there are different stakeholders that are involved in it. So like there is a bus, like then there is a public transit like rapid transit stakeholder, then there is a like Ola Uber stakeholder, then there is a maybe like other stakeholders like the public bicycle operator stakeholder. How you are going to repay them at the end of the month? You collecting a weekly based payment system or like monthly based electric based payment system, but how you are going to pay back to them to the stakeholders at the end of the collecting of the month from this kind of demands. So that is the one of the, according to me, that might be the one of the biggest challenge actually so to be addressed. So when you are taking up this kind of the information, like you have the suppliers, see how many different transport suppliers they have there. So like
Here it is. If it acts like only a platform, then we can make the payment to the authorities. Otherwise, this problem will happen. And you see,
that's the reason I told already. You can assume that level 3 has the booking also, payment with the booking. So once you made the booking with the payment, then obviously all stakeholders are involved as the transport suppliers. So then they are coming in the play so that okay, you will understand now. The point is here, I made a trip by multiple suppliers, like okay, start with the bicycle, public bicycle sharing system. So my home, then I made the trip with the public bicycle sharing system. Then I chose to travel with the bus, maybe bus stop. Then I catch the bus. Then I travel to the maybe like metro somewhere. Then again I use it maybe like kind of the taxi, something like that, the shared mobility. Then I reach my office. So for this trip, I paid almost like the 60 rupees. So all are the different levels in terms of the distance traveled. So I don't have much. What is the distance here and what is the distance here? What is the distance here and what is the distance here? It is not equal, but there are different types of maybe different distances. So at the same time, so like you paid total trip cost is 60 rupees. Then how much money should go to the PBSS operator? And how much money should go to the bus operator? How much money goes to the metro operator? How much money should go to the taxi or like the shared mobility operator like the Ola Uber probably. So now if I made even the small distance like the 2-3 kilometers, then after maybe 8 kilometers, that's still that disaggregated way of doing of your breaking of the money of 60 rupees makes much difficult to distribute the money to the stakeholders, different stakeholders who are involved into the work mass. Any point?
As a mass operator, where the person changed to mode, right? He would get that information.
Yes, obviously.
So if I'm opting for PBSS and I'm getting into a bus, so as an operator, I will be knowing that this person changed to bus towards it, right? If you're able to know that, you can easily estimate the distance traveled on each node.
Okay. You have not understood that one point here actually. So the 60 is the discounted cost. Why it is discounted? Maybe you might be having a monthly cost. To whom I need to cut?
So once you estimate the distance on each node, obviously you are operating on a fixed fare policy. So bus would have a fare policies, and same to the case of metro and taxi. So if you have a fixed fare, if you have distance traveled on each route, uh, I guess you can come up with a nominal cost for
Yeah.
each route.
By looking, it's that easy actually. Such kind of the trips may be multiple, maybe in the millions of the trips can be generated by the millions of the travelers in a day. So then that maintaining of the information of the system of the database, and from that segregating of the again cost will be much difficult. So that's the reason. If you have the more combinations of the suppliers in the transport, like the transit systems, then it makes more and more impact. At the same time, there is the infrastructure cost will be different of the different operators. Like, see, the infrastructure cost of the bus will be different, and the metro will be different, and the PBSs to be operated will be very different. So I need to provide the infrastructure with respect to relevant to the PBS system. So then that cost will need to be paid by the operators. So then he may ask definitely, no, it should be much higher for me compared to you. Because anyhow you are building a road network and you are operating bus on that, but what would be the extra cost for you? How often you are getting the point? So that's the reason. If you want to make them integrate more and more complex way involving of all the operators, so then their need of the infrastructure will be costing or maybe increasing the complexity more. And the other, that is the advantage of the traveler experiences in terms of the availability of the information, then it is the kind of the data and the system integration, and finally the service provisions for the users, then this is the kind of the demand set. So then these are all comes under the categories of the supply set. So then, of course, and after doing of all this kind of exercise, and if no one is demanding of the service, like the mass user, then there is no point to do that. So then these are the kind of stakeholders, users are involved as the sites and the city, and the public transport authorities, and the mass platform providers. So finally, who actually made this platform as a mass, we need to pay to them. Some cost will go very big. So this is the kind of the survey we have designed to one of our students has done. Okay, so then of course we have not modified some of the points in it. Still it is the kind of billion something we kept it, but of course it is not the actual design survey form. So we made that. So what is the kind of user choice when they have the mask? Like we have bundles of the options we have created. The options, okay, if you want to try as the mask, just integrated of the information. That is the first options we have given. Like we have the options of all the options what I have shown as the first case. So these are the different, these are the levels. So for each case of the levels, we started the, okay, you want to know only integration of the information? Are you, okay, if I am providing an app by integrating of the information, are you ready to accept it? So even if you are accepting the mass as the system, first of all, the user should be increased to the mass users, first of all, as the app also. Means we need to download and install. When you are using, then you need to pay for the service at least. So that's the first option. So that is, are you accepting of the integrated information as the mass? Then are you ready to book? Integrating of the information with the booking option. Are you ready to accept it? So then the next option is the passes of the bundles. Which pass of the bundle, monthly, weekly, and the daily based trips, which is the most reliable of the option. Like we have designed so many options of the bundles, then we have categorized into the like the public perception about that. So what the kind of the public perception, attitude, the behavioral control, and the social norms. Suppose the social norms data we have taken into account in such a way, like if you friends are like the relatives of somebody are interested to use this kind of the mass app, are you ready to use that? Something like these are the different kind of these options we have given. Then we have done the different kind of the models with that. So this is the kind of information we have collected, social demographic information. Of course, this is the very basic data. So the traveler characteristics, including of the questions about the mode commute. So generally, what mode they are currently commuting mode, and the frequency of the trip, purpose of the trip, the average travel distance and the times, and the mobility situations of the respondents such as the driving license, ownership and the ability to drive, and the attitudinal indicators questions like the usage, sorry, regarding the technology usage, convenience, like whether they are using any kind of a technology relevant to the transport system and the convenience, price, concerns, time cost. Because when you're using the kind of the apps like the mass, then the data is open to the providers, stakeholders, generally. Because they know that where you're coming, where you're going, everything. So some people very much concerned about such kind of information to share. So then they are not that ease of technology users. Actually. So that's the reason the technological uses we have taken out. And the mass descriptions, like the expectations from the mass and the stated choices of experiment. So we have designed a stated preference questionnaire designs respected to the what are the options we have designed at the initial stage. So these are the kind of the data we have collected. So mostly the data study location is the public places in the Hyderabad, like food courts, metro stations, and the colleges. And the data collection method using of the Google form. Of course, the form is designed in the Google form, but we have taken the offline face-to-face service in general. And the data collection mode is offline, and the total number of samples are collected as 930, and the number of samples finalized. So almost 127 samples are out because of the ambiguity involved in the question, like the respondents' information. So of course, we have also taken out the one question as the willing to adopt the mass, like kind of the two categories as the yes or no, as well as the are you willing to adopt the mass system, which is integrating of different categories of the transport system. Are you agree with that or not? Like strongly agree to strongly disagree is also taken. So. You have any questions on this? Going to share a kind of Excel sheet, like kind of CSV file in the group. So you can also try like the consistency issues with respect to the data. After showing some information inside.
The slides and also the data sets and codes are provided. So there is a folder here for linear regression and India data. You can download that data. So I'll directly show you the data file here. So this is the Redshift sample file I uploaded. It has about I think 1200 records for we have 2400. So again, we can use SPSS to get the data, or you can use R if you prefer that. I just want to show it to you in SPSS. I prefer to use that one. description of the variables is provided in a separate node file. So we'll refer to that as needed. So basically, this is the data view, and SPSS, if you have not used, it's like glorified Excel. It looks very similar to Excel, just that you have two sheets. You have a variable view and a data view. This is where all the data from this file is provided. So you have the stop, the route. This is a combination of cluster ID and stop ID. So for you, the important variables you need to look at are y and log y. These are hourly demands in the peak hour. Okay. So what we'll do is we'll do some models analyzing how log y, which is the demand, because we can start looking at the y also, but y does not look like a normal distribution. That's why usually we take a log. So let me show description of this. So let's look at descriptive. So the simplest thing would be doing descriptives. You can look at y, for example, like we have these. You can look at the data set and come up with it. So you'll see that the mean is for y is about 28. The range goes from 1 to 3. Okay, so all of these stops have some ridership. I think they added 1 to the ridership numbers so that if they take the ln, there is no ridership which still remains 0, okay, not infinity. So that's why these numbers are like that. So the minimum is 1. That doesn't mean every stop has ridership, it's just that it is actually y is ridership plus 1. Okay, and so because of the range, when you have such a large range and a lot of them will have zeros. So if I do the frequency for this one, and we don't want to do frequency in general, but I'm going to just show you for if you look at y, you'll see about 4% of data have 1. So very few of these stops actually have zero ridership, which is good. So you start looking at some of these characteristics once you're given a data. So it's possible that if you're looking at low volume systems, you'll have 30% of the stops will have 0. If you're looking at any system of transit in the southern part of the United States, for example, probably 50% of the stops will have zeros. So depending on what system you're using, the method we use will change. Okay? Because if you have a lot of zeros, you need to figure out how to handle the presence of extra zeros. Here there aren't a lot of zeros, so we can directly use. So you can also draw histograms if you want to see that. And you want to see the for the log y variable, again, the good thing about the log y variable is it narrows down the range. So instead of going from 1 to 332, we now have a variable that goes from 0 to 5.8. So then we can start adding independent variables to understand. So when we are looking at a linear regression model, what we are doing is we are saying the ridership variable, the dependent variable is a function of other independent variables. So you are writing y is equal to beta x, and you are trying to find your betas. Okay, so we'll talk about the exact mechanism of how to find the betas in the class in the next session. But here I want to show you how we can do this. So I created a this is again, if you have not used how many of you have used R? Okay. So what I'll suggest is go ahead and install R Studio and R Tools, and then you will be able to run it. So I'm giving you the code, so you don't have to code anything. You just open the file. If you installed the software R Studio and R, it will work. So just look at how to install R Studio. A lot of things on YouTube or on Google, you can find that. So just install that, and then here I'm providing you different approach. So this is where you will provide the name of the data. Okay, so I gave you the CSV file. You just have to. It's already there. So you it should if you have the code, the script and the data set in the same folder, and you download it, both of them will be in the same folder. So it should automatically access that. Otherwise, you can change your directory, but usually it should pick it up on its own. So you can do the first thing I'm doing is just doing the means of the data just to get an idea of whether the data loaded correctly or not, and then we can do a lot of recoding on all of that. But this is the linear model. Again, I will explain how to interpret this for now, I'm just giving you a structure. So this is your dependent variable. And then I'm identifying 5 or 6 independent variables. The way you specify your linear regression model in RStudio is simply LM is going to let's say know that it has to do linear regression. This is your dependent variable. And whatever you want to use as x. So y is equal to beta x. X can have x beta 1, x1, beta 2, x2, and so on. So these are our x's. Simply that. Okay. So if we have this. So this is the model out. So it's running the linear regression model. So this is the dependent variable. These are your independent variables. Again, I'm just giving you some random variables here. You need to look at what these variables are, interpret and all that. So basically the code will run. So now what I will do is even before you run this model. So this is how you can run a linear regression model. But even before you run this model, I want you to look at the distribution of the variable. So if you look at the different variables here, there are what's called there are frequency variables. So if you think about ridership, right? What is one of the most important variables in modeling ridership? If I'm let's say modeling stop level ridership, what would be the most important variable in modeling ridership? But for let's say I want to model ridership for 3 hours, the peak hour. So what determines ridership the most? Accessibility. Any other thoughts?
Frequency of time.
The transit service frequency or headway between the right. If there's only one bus coming, you can have all the accessibility you want. The people are not going to. So accessibility is important, but I would say the primary factor is frequency. How many buses go through that stop in that 3-hour period is very important. Now, is that a truly independent variable? Because every transit agency, when they're determining the schedule, it's not like they're going to put a bus every minute in the part where there are no people, right? I mean, if there is a rural location where there is probably 5 people who want to use transit, it's not like you send a bus every minute. You have high frequency locations, high frequency services in locations where there is going to be high frequency demand, right? So it's like a chicken and egg. So we have very high demand. So there is very high service. Now, if you run a model, you will say, oh, if there is a very high frequency, there is high ridership. That's not true. So you have to be careful. So whenever you look at any literature, any paper, they will say frequency is very important. Yes, frequency is very important. But what about the transit agency's thought process in saying this is a route where we will have a lot of demand? There is what is called self-selection. Frequency is a self-selected variable. Because we know a lot of vehicles, a lot of people will use the bus at that facility, so they put high frequency. So it's not a truly independent variable. So there are ways. Again, for now, let's ignore this issue. We'll talk about how to handle that. It's a complication on models, right? When you look at any linear regression model, y and x should not be correlated. You can do y equal to beta x only when y and x are truly independent. But again, this is an example where it's not the case. Your headway is determined because you expect some level of ridership. Okay, so there are ways to correct for it. We will talk about that. And here, there are different variables. I'll show you here, for example. So this is the frequency. So the variable subfreq is basically frequency of the subject route, and it captures buses per hour. So there could be 2 buses, 6 buses. So let me show you the distribution of that variable. Yeah. So again, less than 1 for a lot of records. So you will see that the number of buses per hour for some of the stops is less than 1, which makes sense. But then as you go up, you go to 2, even 3, up to 16. Okay, so what we are seeing is there are some stops where you are getting 16 buses in a 3-hour period, but there are some stops where you are getting much less than. Okay, so this is a linear variable, right? At some level we have a continuous value, but one could argue that there is some potentially non-linearity in the impact, right? So if the number of buses is up to 1 or 2 per a 3-hour period, it's like it's coming only once in that whole time period, right? You can say that the frequency is 0.4 per hour, or in 3 hours there is 1 bus, right? Pretty much. So the impact of frequency would be non-linear. So up to some point, frequency has a linear impact, but then it can go up. So when you know there are 3 buses every hour, I feel more comfortable using that system, because I know even if I miss one, I just have to wait for a few minutes, I get. So it could be the impact of headway could be non-linear. So that's why they created these 3 variables. So they have 3 separate variables. These are called spline variables. So if it's 0 to 3, it's exactly the same variable. There's no change. If it's 3 to 6, you have frequency minus 3. Okay, if it's more than 6, you create minus 6. So these variables are created to see if there is an additional impact of higher frequency. So this is linear up to 3. After 3, this still continues. This effect still continues. There could be additional effect for 3 to 6. If you look at the third one, this continues beyond 6. There is additional effect beyond 6. Okay? So this is called a spline model. So you can think of this as a way to capture, maybe if you are between 3 and 6, on top of the linear effect, there is an additional linear effect. Okay, because it is more, or it could bring it down. It could be positive or negative. The effect could be positive or negative for these 2. So if it's positive, what it means is, if you have more than 3 buses coming, the jump in ridership is more higher than just increasing from 3 to 3.1. So when I move from 3 to 3.1, there is positive effect from here. There is an additional positive effect from here if the coefficient is positive. The coefficient is negative. What it tells you is after 3, people don't care. It actually does not contribute as much to ridership, but we'll let the data show. Okay, so this is that. This is the same kind of variable, but on top of 6. So instead, so the way it's characterized. If you just have, this is, let's say, the frequency. So if frequency increases, you are increasing rate. But what I'm going to do there is I'm saying at 3 and at 6, this slope can change. Maybe it goes up like that, up to 6, and then maybe it lands up. I mean, there's only so much number of buses can do, right? If you're getting 12 buses or 15 buses, maybe it doesn't matter after a point. So what that means is you will hit the maximum at a particular point. After that, it just tapers down. There's no additional benefit. So to a particular stop, if you get 6 buses or 7 buses or 12 buses, it's the same effect as getting 6 buses. It could have again. So this could be potential case. So what we are doing there is we are saying the slope changes at 3 and at 6. It changes. So now this change could be positive, or like I'm showing the way I'm showing it here, it is negative. So what that means is it goes linear up to here, goes up, and then tapers down. So you can think of this as a relationship like this. But figuring out this relationship is complicated. But if I break it into pieces and say, okay, this is a line, this is a line, this is a line, I am specifying these 3 as small lines. So you can see, you know that based on what we learned about polygon, any polynomial figure can be approximate it with lines, as long as you take enough lines. Okay. Obviously, you can take more lines. It will just increase our burden. So here, what we are doing here is we are saying this is a non-linear curve of relationship with frequency and headway and ridership. So we are plotting that relationship. Typically, what you do is you make an assumption it's linear and you do only one line, which most of the time is off by line, right? Because it's not possible that if I keep increasing frequency blindly, things will happen. And also, at the lower range, maybe frequency does not matter. If whether you have 1/10 of a bus coming an hour or 1/20th of a bus coming at an hour, if it is less than 1 per hour, maybe frequency does not really matter. In that case, maybe people decide to take the bus purely based on accessibility and need. Okay, so to assume that this whole thing is linear sometimes can be wrong. So that's why we can try different structures where we allow for a piecewise linear function. This is what is captured. So the variable creation described there is a very efficient way of doing it. It actually does not need a lot of work. All we are doing, instead of doing beta times frequency, you create 3 variables like this, and you have a piecewise linear function. And these variables can be created very easily. The code is here. All you are doing is this, you don't change anything. Okay, if observed frequency is less than 3 buses, it's per hour is equal to 3. Yeah. So if it crosses 3, this stops at 3. Okay. Now this one will have frequency minus 3. Okay, all you're doing is taking off 3. And if it crosses 6, it becomes 6. So if it is between, if the frequency, let's say, is 4.5, okay, this value will stop at 3. This value will be 1.5. This value will be 0. If the frequency is 7, this value will be 3, this value will be 6, this value will be 1. That is how you create these 3 variables. Okay, we are just converting the single column into 3 columns following this logic. So if it's less than 3, just copy it, don't change anything, put these 2 as 3. Okay, if it crosses 3, this is simply 3. This will be whatever is the value minus 3. If it's more than 6, just make this 6 and go. You change. So so basically we are creating 3 categories of variables which handle the 3 regions that we are interested in. Okay, so that's what is being created. Okay, and then there are a lot of other variables that they created. I think you might have to look at the paper for fully understanding all of these. So they are looking at, they looked at the network and identified if there are competing routes for that stop, okay, or complementary routes. So they created these variables for us. Okay, so we can look at how many fully and partly complementary routes. So again, all of these might not be significant. Maybe 1 or 2 of them can be significant. So this they put an effort in identifying at the stop level what is the interactions on the network. Then there is also interactions with metro. They looked at how many of them are complementary, how many of them are competing. Again, this would require a lot of work to figure out which routes are actually complementary. Because again, there could be partial complementary nature. Partially, if you have a bus route and metro route that's perpendicular, then you can say that they are complementary. Right? If there are both of them are parallel to each other and are covering the same neighborhoods, then you can start saying they are competing. So depending on that, I think this was a subjective classification of variables. So it must have been a lot of work to figure out which routes are complementary and which routes are parallel. Then they also looked at access to downtown. So they looked at number of downtown stops, downstream stops that were accessible from this stop, and so on. So they created these variables. They also had some stop level variables. So they had plan of population, plan of employment, commercial, industrial. They would have tried, and I think these are the variables that ended up being significant in their models. Okay, so basically the idea is you can start looking at some of these and consider adding them in the model once we go through it. Again, I'm not asking you to try it out yet. Basically, this is the formulation. The formulation is right here. You can pick the variables from that file and put them here with a plus in the middle. These are your x, x1, x2, x3, x4. It will automatically add a intercept and run the model. Okay, that's how you can get the coefficients. So these are the coefficients here. So what this tells you is between the variable 0 to 3 has a coefficient of 0.66. It's a positive coefficient. What that means is if the frequency is higher, you will have higher ridership in this case, as you would expect. Any questions? Okay. So you can also look at the other codes. There is binary logic, multinomial logic OL. Again, I will go over all of these in class, and maybe because we not finished that part of it, we can look at that. And another thing I want you to do. Some time to let me. You get 2 slides from module 2, so I'll finish it so I can start methods in the next class. We'll be a little ahead. Again, this is building on what Dr. Agram mentioned. So again, we need supplementary data. When it's not enough to just have ridership data. If you have ridership data, that's our dependent variable, right? That's our y. We still need the x's that we need to look. So some of the attributes that we need are transit system operational attributes. So average headway. Or again, you can introduce this in different forms. You can use it as a headway, which would be gap between two buses arriving at that stop. Or you can look at frequency. You can convert that as a reciprocal of that and say in an hour 3 buses are coming. Or you could use the minute. So it's up to us on how we want to decide. Accessibility indices, we need information on transit accessibility. So how many bus metro train stops are there? How close are they? And what is the length of bus metro train lane within a ward or within the zone and so on. Then transportation infrastructure is important. Roadway length by functional classification. So you can look at how many expressways are there, how many arterials, collectors are there, what is the bike lane length, and also finally distance to central business. All of these are important. And other things such as number of parks, area of those parks, residential area, commercial area. Again, it could be commercial parcels or area of commercial parcels, retail, government, distribution. Again, depending on whatever information is available, employment density. There's another metric called walk score. I don't know if an equivalent metric is available in India, but basically what it represents is how walkable is that neighborhood. Okay, so we would consider whether there are sidewalks, whether there are traffic crashes happening, safety is mentioned or not. So based on that, some of these things we can. So this is an example list. This was one of our older papers in 2016. So it's already 9 years now. So we looked at these groups of variables. So we have stop level variables. So we were modeling ridership by time period. We had ridership for the AM, PM, off peak day, off peak night. So there were a lot of time periods, weekday, weekend, and so on. So we looked at headway. So this information is not always easy to get. So sometimes because bus frequency changes by time of day. If the agency that you are working with has that information, it is great. So you can then incorporate that. We had that information. We looked at how many bus lines are passing through each stop. So the number of routes using the same stop, we looked at that. And if there is a night bus that passes through stop. So these were some variables we looked at for the stop level variables. Around the stop, transit variables that we looked at included number of bus stops, metro stops, train stations, bus line length. You'll see that the meters change because these are all the significant variables. So we tried 200, 400, 600, and 800 for everything. For all of these variables, we tried all 4 buffer sizes, and the values I'm showing here are the significant values. Okay. So here, bus line length, and as all of you students know, most of the work was done by my student. So he is the one who ran the models for all of these variables. And so 200, 600, and then we also looked at metro line length. this is a TSB variable, so this does not change the buffer set, right? So because we did not have it in the, we used that as a better indicator for us. We also had reserved bus lane length, and then we also looked at infrastructure around the stop. So the major road lengths, highway length, land use. So you will see park area in different buffers, number of parks, commercial enterprises. So all of these we looked at in as independent variables in our model. Okay. So again, it's always good to have an exhaustive set of variables that are possible. So if you don't have a particular variable, obviously you cannot consider it. So if you have that variable, if the JS layer is available, you can start looking at that from that perspective. Okay, so we did a webinar for creating like some sound. How we create these variables. Again, the slide deck for this is also available. Just again, I know some of you might do this already, know how to do this. Some of you might not have looked at it. So he's the one who does this better than me. So I am doing this video for you.
Yeah, property change. So how can I define jobs? Jobs can be defined as the number of jobs as known from points. The employment data for the University of London in 2016 was strong. These data contains information on the employment of individual aged 20 through 64 years. These data were partially included as a structure file using the unique and created by continuity in census records. Now, let's discuss the case section dispute. In our study, non-CUT was included using jobs.
So here what we're doing is we're computing job accessibility. So instead of a static buffer, we're actually looking at if you start driving from that location, how far can you go 10 minutes in all directions? Okay, so it won't be a circle that way, but it's a network distance that we use.
We use the minute runtime for our device as the aggregate threshold. The driving distance was computed using the day period, and it must have been considered 8 a.m. on Wednesday. State network of Korea has been used to draw driving area for both driving time and distance. 2011, to the existing state network of University data was used in Austin. So, to estimate the driving time, we use state network.
Maybe 5 minutes we'll finish it.
we define speed to be the speed for a street from the input points category. In our network file, we have each categories, and we will select a fixed speed for a particular speed category. For example, if the speed category is 65 to 80 miles per hour, then we will consider the speed as 70 miles per hour for that particular speed category. So that is our network shape file that is speed. If you open the data unit for the axis, you will find a speed category, and based on the speed category, you have to create a speed column. Then you also create a length column, create the name of the stream in files, and once you have the speed and the length, you create the carbon diagram of each place, and they need to be those. Then you will create the network, create the network on your analyst on this, and you have to follow these steps. First of all, you have to go to Windows, that's a catalog. And once you open the catalog, you will get the road network shapefile. So this is the road network shapefile, that's speed. And then you have to right click on the shapefile, and you will find new road network dataset. And you have to select it and follow the steps as we explained in detail in version 1. And once you complete all the steps, you will create the network in ArcGIS, and finally you find those new layers. First layer is the mesh layer, and the second layer is the case layer. And now you have to get the telemeter distance from the network layer. And this is our final case area of the telemeter area. So to create this, follow the steps. First of all, network analyst, select new service area, and then make new layer in the service area. And after that, you will find facilities for your lines. And first of all, you have to load the facilities. So you have to go to location, and here select the station. Once
So here we are doing the network around metro station, commuter range stations. So we wanted to identify a 10-minute accessible area around 10 minutes by driving distance. So that's what we're trying to do. We're not just drawing equal distances, but we're drawing driving distance. And then if you are examining these as locations affected by commuter. So we wanted to look at areas, property values in that, and also traffic congestion and other things. But we wanted to look at how property values change for homes in this 10-minute driving area versus the rest of the city. Because they are, again, this is the influence area of the train station versus if they're outside the influence area of the train station, how did the prices change? Because in Florida during this time, prices increased everywhere. So we wanted to identify a control and a case. So we wanted to identify where are property values changing because of the train station taking OD versus locations where, okay, what is the baseline change? If there is a baseline change of 12%, if your areas around public transit only change 12%, then there is no increase per capita. So that's what we wanted to control. So that's what we're trying to do.
We have to edit the property of the service area. So to go properties, and you have to provide the impedance. Impedance will be the minutes. Then you have to provide default break. You have to put 10 percent set in 10 minute per distance. And then you have to provide the time to day and date to week. And then the 17 polygons here. Now we have to solve it. So we have to click the solve, and once it is solved, you will place it here. You need to export the layer, and the exported layer will be basically. Now select the control area. In our study, we selected 20 to 30 minute time as our auto threshold. The census tract located within this 10 minute threshold area were selected to the immediate control. Here, the blue region is our auto threshold. Control area selection procedure is almost same as the base area. Here, we put 20 and 30 minutes before break option instead of 10 for case area.
So what we're trying to do here is 10 minutes in the influence area, we said. So we wanted to find similar houses or similar properties away from 10 minutes. But at the same time, we did not want to go too far. So we said we look for time window between 20 and 30 minutes from a station. So we created an area. So this green area was excluded because this is the 20-minute boundary and the blue area is the 30-minute boundary. So
For all the speeds,
So we did it for multiple speeds because the roadways are different speeds. Right? When you're going from here, for example, they're going from here to here. Some roads will be 20 minutes, some roads will be 40 minutes, some roads will be 50 minutes. So the speed limit, the initial table that is created, that is to tell if the link road speed limit is 40. We assume average speed is 35 miles on that link.
okay, so that speed you are creating.
That's why we're getting out 10 minutes. Yeah, so based on the assumed speed, we can get a time for each link, right? If the link is half a mile and the speed limit is 50 miles, so we're assuming 45 miles, so we get a time to traverse that distance. So again, whenever we are doing network distance, we need to figure out some way of capturing speed. We don't know, we don't have data on speed for every, right? So we are assuming, making some assumptions to get that time. So we are not blindly assuming the same time, same speed for the entire trip, right? So we are assuming based on the speed limit on that link. Yes, it could be different. Some people go higher, some people go lower than speed limit. But at least we are not assuming average speed is 45 when only 20% of the trip happens on a 40 to 50 speed, right? So that's the reason for this.
So when you edit the properties area, we find that default rates, and in case of case, we provided K here, but here you have to provide 20 and just press OK. And the remaining steps will be exactly the same as the case area. And now we have generated the case area and the control area. Then you have to calculate the geometric chain that will follow the steps of the property value change we have discussed here. And for the other is the procedure.
So this project again, the link is available online. The report also has very good details of how we did all of the GIS work. If any of you are interested or looking for resources, this would be a good source for you. That's why I wanted to show this. So in this project, we did how job accessibility changed as a result of a commuter rail project that was completed in Orlando. So the commuter rail had 15 stations. When we look at different benefits, we looked at how commuting time changed, what is the transit travel time savings from the project, okay? And what is the value to the community because of changes in property values. So across most measures, the addition of commuter rail did not make any difference. If you look look at the change in condition, they had about 4,500 riders per day. Okay, so in a city like Orlando, that does not add amount too much. I think the travel time improvement was like 0.001 minutes or something like that. Because you're only taking 4,500 vehicles up. You have millions of vehicles on the road, so that doesn't change. So over using every metric, the project was a failure in terms of additional transportation. But if you look at the change in property values, the value addition because of public transit. In the US, especially in the southern part of US, people don't like to use public transit, but they like to live around public transit station because it brings in accessibility, right? There is retail, shopping that comes around that, a lot of condos come around it, the property values. So the three counties that funded the transit agency, so the funds for the commuter rail, some of it came from federal, but everything else came from the counties. So three counties put their money, and we were able to show that they're actually getting the returns back because new developments have come around these transit stations. So which were vacant before. They were not paying any property taxes before. So the counties were getting no income. Now they put in money to fund the agency, fund the train station. But now because of the stations, a lot of new developments have come up and the revenue generated for these counties is substantially significant. To the point that there is a positive ROI for the investment. So again, whenever the reason I mentioned this is whenever we look at transit investments, especially in the Western world, we focus on transportation impacts. Yes, there are transportation impacts, and we want them to be significant. We want them to be large. Right? We don't question that. And it would be nice if 100,000 people are using that transit service, the commuter rail service. But even if that does not happen, there are other non-transportation benefits that can outweigh the costs that go into building that infrastructure. So, if we can convey that message to people who live in these regions, they will recognize the value of transit. Again, the reason public transit is not used well is because it does not serve many locations. What it does is it connects one part of the city to another part of the city only during peak hours. I mean, but people don't just think about life in the peak hours. They need to go there. If they end up working longer, they don't have a car suddenly, now they have to come back home. They went to the train in the morning, but if they cannot get out of work on time, that psychologically does not encourage people to use public transport because they're like, yeah, it's there from 3 to 5. If I get delayed, I can't go. So again, these are some challenges. So, but there are a lot of non-transportation benefits that allow for bring a lot of return on investment. So I think some of the methods we show. So this project is here. This is the project. So we evaluated the community building effectiveness of transportation investments. So it's a three-phase project we did for the Florida Department of Transportation, and it was predominantly looking at using GIS to figure out how property values change, how can we identify job accessibility around a station, how travel time has changed. So these are the different aspects we did. So if you are interested in GIS-based resources, you can look at that project.
In this contradictory that on one hand you are saying that the property value change and there is settlement and there is change in land use around the area. And there is no significant change in ridership across the country. So either one should be the consequence of the other, and if it doesn't happen, that shouldn't sustain. I mean to say that, for example, there is some expectation that there will be a lot of activity and there will be a movement across that line. And that
takes time. Right? It takes time for so new communities are coming. So they're just moving there. You have to be patient to see ridership change. It will change. It will grow. There will be, but it's not necessary that all of those people are working in the route. So this is a north-south train station, train corridor. It connects 13, but Orlando is like 60 square miles.
So maybe the gestation period will be longer and we need to wait.
It is possible. No, I'm saying I don't care what is the ridership for the future also. Even without that, just building those stations is creating revenue for the counties because it becomes a center. Those stations become centers of activity for different reasons, and then retail and establishment comes. That doesn't necessarily feed into transit. Again, I cannot help with the culture. I cannot help with why people are not taking transit. We cannot change that. But you cannot focus purely on transportation benefits and say this is working or this is not working. You also have to look at a holistic evaluation is necessary before you call a project a success or a failure. That's what I mean. Yes. Again, there are a lot of mistakes they are making in the industry. So they say they are not increasing the train schedule beyond 6 p.m. in the night. And it's true. In Orlando, in summer, it gets dark at 8:30. If people don't even realize it's 6 o'clock before even when it's 7 o'clock. Also. So what I'm saying is, and there is no coordination of Sunrail with the public transit system. The buses, there is no coordination. Like, there is a bus comes 5 minutes after the Sunrail leaves, and there is only one Sunrail every 20 minutes or 30 minutes. I mean, how hard is it to coordinate? But they don't do it because again, there are politics. There
There
are
is kind of surrogate investment to make property tax.
yes. So if you are the county, if you are a county that is putting in money, you should go ahead and put money because you are bringing something that will increase your revenue substantially. Yes, transit numbers might not be that. So but it's still a valuable investment for counties where there's a lot of rural population, and suddenly this comes in, people don't look at this as rural anymore. They look at it as, oh, this is a hub. We can actually live around this. So developers come in and build apartments and homes. Because again, it's a little different than in India. In India, space is a premium. In the US, it's very different. You can buy 1,000 acres for a very little price. Unless there is a home or a resident retail unit there, there is no value for the land in that part. So that's the change. Okay, so yeah, we take pause. Yeah, I think we can get to. Okay, thank you. So please download the data and get so we
already have the
okay, then it's great. So we can start working on the boards there. No, not today.